Okay guys, good morning. The first part of today's lecture, we're going to continue our discussion about the principle of the database system in general, okay? Then after that, we're going to go over with more details about the relational data model, then talk about one of the query language. In particular, we're going to talk about the relational algebra. So just a quick review. Last lecture, we talked about the data model. So what's the data model? What do you mean by the data model? Is the way that we're going to use, or the structure that you use in order to describe your data on database. Yeah? Then, of course, we're going to use schema in order to describe the particular design that we're going to use. So, for example, I'm going to use the relational data model. So what does that mean here? That means I'm going to take my data and represent my data as tables or relations. Okay? Then I'm going to use a schema in order to write the exact description of this collection of data, how it looks like. So I'm going to, for example, assume that we have a relation, and this relation called, give me a second, let me try to use, I think I can use my iPad, hopefully. To assume that we have, this is the schema, my schema, or the structure, or relation data model we're going to use. I'm going to say, for example, I have a student. Then maybe you have another table who's going to contain information about the instructor, etc. So I'm going to use the schema in order to what? To describe this data itself. After I choose whatever data model I'm going to use. So a schema here for the student, I'm going to say, what relation do you have? Then you have to exactly tell me what the content of each relations. For example, this relation is going to have the student ID and what's the data type. It looks like you define all your variable on your programs. Okay? First you choose the programming language, then after that starting to write your query or your, let's say, command or whatever instruction using this language. So what's the instance? We talked about the instance last time. What do you mean by the instance? You didn't expect me, I'm gonna ask you questions, yeah? Just I want to make sure that we're on the same page. Anyway, the instance, that means the actual content of the database at a specific point of time. For example, if you have a relation, you use whatever data model, assume that a relational data model, then inside this one I'm gonna decide, or the structure, I'm gonna have a student, gonna have instruction, etc. What's the content here? What's the actual data that's gonna be stored there? That's what is called, the instance. More details today. When we finish the first part, we'll start the second part of today's lecture. We're gonna go with more details with the relational data model, so I'm gonna review this one again. Okay? So last time we have said that in order or for the system going to be usable, okay, it must retrieve data efficiently. Which one is the main goal of using database management system, right? We still remember last time? So anyway, the developer is going to do what? It's going to using complex data structure in order to represent the data in the database, in order to make it easier for user in order to use them, or make it more efficient to access these data. Right? Generally speaking, the developer is going to do what? It's going to hide this complexity in order to use the database management system as the normal user, and even as a developer, the programmer. So you didn't need to know exactly what's going to happen in the low level. For example, how the data is going to be stored, whether if you change different operating system or using, for example, another computer, you don't need to be worried about anything at the low level. So just focus on the high level. As a user, what I need to log into the web page. If we have a web application that has a back end of the database, just type whatever information that you're looking for, username and password, or just navigate my way, then I get the result. I don't care whether I need to take, for example, understand how the data can be stored at the lower level because I'm using my desktop or my using laptop. I don't care. Even as the programmer, okay, you don't need to worry about the low level. The only thing that you want to worry about, for example, the view level and the logical level. Yeah, remember last time we said the developer is going to do what? Hide this complexity, whatever, that in the low level in the database from the users through several levels of abstraction. And we talk about this one. We said we have like a physical level, the logical level, and the view level. Okay, so it looks like we have a clear separation between the logical and the physical layers. Okay, the logical, that means, here in this case, for example, what tables, assume that we have the relational data model, so it's easy to work with. What tables are there? What attributes do you have? And also what the constraint that we need to enforce in the database. In the physical level, how you are going to actually store the data on the disk. So if you take a look to the disk in the low level, so I don't care about, for example, if you have this file, I don't need to know exactly how the system or this information is going to store in the disk. For example, it's going to be has a blocks, and each block of the data is going to be organized based on a specific way. So I don't care about this. Okay? And that's what we talked about last time, if you still remember. There's one thing else here. Or one important feature of the data models that we're going to use here, such as a relational model. They are going to hide such whatever low-level implementation details. Okay? From not just the database users and the normal users, but even from the people or the database application developers. Okay? Good. So what do you mean here? We have what is called physical data independence. That's what I mean, like give you an idea what I'm talking about, okay? So here the concept here, the applications or the user at the high level don't need to worry about how the data can be organized at the low level. Let's ask you a question when you write any programming language. Do you want to get a care, for example, when you write your code, how the data will be actually stored at the low level? How the data, or let's say the operating system is going to take care, for example, every time we try to open the file or close the file or store the file. Do you care about what's going to happen at the low level? What kind of, let's say, the input output calls from, let's say, from operating system to the disk in order to retrieve the data stored? No, everything is going to hide. The compiler is going to take care of this one, yeah, on behalf of us. The same thing here. So here, what are we looking for? So that means if the application don't need to worry about the low-level implementation, in this case, we can change, for example, where, how, whatever database component, or let's say database, objects are presented at the low level. So that's what is called here the physical data independence. So here, remember, the physical, that means where the data can be stored in the disk, and you have the second level, we call this one the logical level. So here, for example, you can assume that we have the relational model. So you have like tables and the relation between each tables that we have. Okay? And here how the actual data is going to be stored on the disk. Okay? So here we have what's called physical data independence here. That means here, regardless of the low level, regardless of whatever the computer or the operating system going to use, this one is not going to affect the application going to apply or that you have. The application going to do what? When you write your application, is going to be depending on the way that the data is going to be organized here, or the structure, whatever relational model that we have. For example, when you write your application here, you need to know what's the name of the tables that we have, what the actual attributes inside the tables. You don't need to be worried, for example, if you move your data from one computer to another computer. It's supposed to be this one, it doesn't affect the application itself. For example, if inside the computer said, maybe we're gonna convert the way that we organize the data here using different data structures. We cover this one in more detail, CS525. We can use heap, store files organization in order to store the data on disk. We can use a tree structure. We can use hash table or hash structure. Structure or file organization. So the way that organize my data. Remember, we have a different data structure. We can use them in order to organize the data in order to help us more efficient, or provide us with the way that allow us in order to access the data more efficient way. So here, take a look here. If you move, for example, you have one hard disk to another hard disk, this one's supposed not affect your application. So this means you're not gonna change your application high level. You're not gonna change, for example, the logical level of the data, the structure. How the data or relation is gonna, connected to each other, and at the same time the attributes. Hopefully this one is clear for you guys.
So the examples are changes. So what do the examples represent here? The 4 examples.
You mean here, this slide?
Yes.
Okay. So assume that I'm going to use a relational model, a university database. What type of, how many, let's say, relations do you have? Or tables do you have? Maybe you have table contains information about the student, okay? And another one about the instructor, okay? So I'm gonna do what is called the logical level. That means here I need just to define what tables are there and what the attributes should they have. For example, maybe have a student ID, name. Okay, and the instruction might be the instructor ID, name, and etc. This is clear? And you need to find out what the relation between student and the instructor. For example, let's say simple relation is going to be advice. So this means we have a number of instructors that advise a number of students. Clear? This is assume that it's going to be your logical level. You will use the relational algebra. Of course, I didn't explain to you how can we depict or represent our relational model using this diagram. But assume that's what we have. This is clear for you?
Yes.
Okay. Now, this is what we call the logical level. Now you need to take a look. How could you store these data on disk? So in this case, we need to find what? Every piece of information must be converted or represented as blocks. Did you study operating system?
Yes.
Okay, so how do you store your data on the disk? All the data must be stored as blocks, okay? For example, you have 4 kilobytes each, okay? So that means you take, for example, how many tuples or how many students you have. For example, we have 100 students and we have 50 instructions. So that means here you have 100 records. You want to store them here. So in this case, when you store them lower level, that means you have to tell me how do you organize this data or the actual component or let's say the data on disk. So let's say I'm going to use the heap file organization. Hopefully you study this one operating system. This one, that means you have to convert whatever records that we have that contains this, say, give you an example here. For example, you have a student A123. This is your student name, so the ID and the name Alice and the department computer science. How could you store this record in the disk? It's completely different story. You need to convert whatever the ASCII coded data into what is called bytes. For example, for each record, for example, it requires from you to have 100 bytes. Remember, I have 4 kilobytes, so that means you have 100 bytes, the next, and etc. Okay? If you use heap, that means you are going to store these, for example, 100 tuples randomly in any place, in any blocks that you have in the disk. The physical data independence said you don't need to worry about the way I'm going to store the data here. Okay? If we change, for example, you define your data type, for example, the ID or this is your GPA require from you to have, let's say, integer, for example. Of course, let's say float. Okay? Float, for example, require from you to have 60 bits in order to store one record or field. Okay? If you change or your operating system with the disk is more advanced, or operating system require or change float data type from 16 to be 32 bits. This one I don't care. It doesn't affect me here because this one is not gonna affect, the logical design of my data, because still I'm keeping, say you have a student, you have ID, name. I don't care if I define the ID as a float number or the GPA, the float number. I didn't care how the database or let's say the operating system is gonna store this information at the low level. Either it's gonna have, for example, 2 bytes or maybe you're gonna have 4 bytes. I don't care. Even if you change this one, I don't care. Another way to perform that, sometimes the operating system or the database management system use different way in order to organize these records on the blocks. Instead, using the heap file organization, it's going to use, for example, tree structure, or maybe you're going to use hash. This is not going to affect the logical level. We still have a student, we still have instructor, and each of them they have specific fields and the data type and what is called the way that's going to be laid out of the disk is not going to affect me in the logical level. That's what is called the physical data independence that provided by the database management system. Is it clear? Remember, we try to come up with the different data structures that allow us in order to what? And access the data, modify the data in a more efficient and convenient way. So either have a tree structure or maybe have a skip list or whatever, any data structure. It's like a similar way in order to speed up the access to the data. Because remember, when I'm going to store my data in the low level, here I'm trying to find the best data structure that allow me to access the data so efficient. Using heap file, for example, or file organization, not efficient. Because what I've said, I'm gonna randomly assign or store the data at random in any block. For the B plus tree, no. For the skip list, no. Okay? By the way, tomorrow my office hour is gonna be, I will be from 12 I think 12, 1, 1, 2, 2, 3. Yeah, 12 to 1. I will be available here online. Good. Okay, that's what we're. So the only thing you need to do to understand here, regardless whatever the structure or the logical level, this one is not going to affect you the way that you're going to store the data in the low level, which that's what we need. Okay. Hopefully you get. Okay. Hopefully this one is not messy here. Okay. Good. Now. Yeah, by the way, I can add another point here. Sometimes the database here, when you store the data on the disk in the low level, you compress the data because you have a lot of information. So sometimes you are not going to access the data from long time, long time. So I'm gonna one way in order to save space here, we are going to compress the data. This one again, this is low level. I don't care, as I'm just based on the when you try to access the data or try to design my data logical level. I don't care about how the database management system is going to deal with whatever the data is going to be stored in the low level. Okay. And the other one here, we need to take a look to the database language here. Which one interesting about? We do have different types of language. Actually, we do have the main types, but I add more. Okay. Just speaking with the main types of the database language, the way that just allow you to describe how could you access the data, how could you manipulate the data, how could you create data, and etc. Okay, the main types is going to be the data definition language. The second main type is the data manipulation language. Then we can add more data control language and transaction control language. So I'm going to go over one at a time and explain to you what do you mean exactly by each of them. Okay. So here the first one, the data definition language. Which one? It's used in order to create schema. Remember, we talked the schema is the structure of the database that describes the database that we have, or the data that we have. If you said you have a relation, the name of the relation is student, and it has or contains specific number of attributes, now we need to find a way in order to describe them. Yeah. If you are familiar with the structure in C language, this is similar, the same thing. Okay, or you can imagine that when you create a class, you have the name of the class, then you have to specify the fields or the data fields of this class. Okay, so this is the data definition language that allow me in order to create schema, tables, index, constraints, etc. So in other words, if you said I need to have the data, or let's say department relation that contains department name, building, and budget, how can I create this data? Because remember, we have a diagram. Now I need to create the logical level. How can I perform that? I need to use specific language in order to allow me to execute this one or create the schema in general. Yeah. So we're gonna see this one later, more details when we talk about the SQL. But just keep in your mind right now the data definition language, the language that is responsible in order to allow me to define the database schema, which tables, index, constraints, etc. in the database. So you're gonna see, maybe you're gonna see have create, maybe you can say alter, you can drop. Sometimes you have a relation, then later you decide that the relation, I need to remove this relation, I need to add maybe another, let's say, attribute to this relation. For example, we said in the department, maybe we need to add another attribute that capture more information in this department. So in this case, you can modify your schema, you can delete it, you can delete the content, whatever the schema that contains information, etc. They're just only responsible for create schema in general. Okay. The way that you perform that, we are lucky. We are going to take a look to one specific language. It's called, structured query language, which is either SQL or SQL. Okay, which allow me or provide me with the way in order to specify or define database schema. So SQL is going to contain the part that's responsible for the data definition language. Allow me to create schema in general. When I say schema, by the way, this means the tables, the index, the constraint, whatever else, okay, in general. Good. That's the first one. The second type of the data, we call this one the data manipulation language. So the data definition language just create the schema, the tables, etc. We have another language that allow me to what? To manipulate data. When I say manipulate in general, that means I want to insert new tuples. So for example, if we said we have instructor table, now I need to add a new instructor. What does that mean? New records, new tuples. For example, instructor ID, name, salary, department, etc., whatever information you need. How can you perform this one? I'm going to use the data manipulation language. Again, update and modify or accessing the data. For example, how can you retrieve the data? When you say retrieve the data, that means you are going to access this table, then you are going to extract some information. For example, I want the list of all the instructors that works in let's say in the computer science department. So that means I'm going to use the data manipulation language. SQL allow me in order to provide me with some tools, let's say, or some commands that allow me in order to express whatever query I want to perform. The simple thing you can think about, we can say select, let's say star from instructor. That means give me the list of all the instructors stored in this table. Okay, that's means you can use select. Good. Sometimes we talk about the query language, but this one take it away from the data manipulation language. Some textbooks they said we have data manipulation language that allow you only to update data. When you say update, this means delete, modify, yeah, or add new, insert. And they put the query language as different component or different language, separate language. I don't prefer to use this one. I prefer to use the data manipulation language at the top, and they can specify data manipulation language allow you to access and update the data. When you say access, this means I'm going to use a specific notation. I'm going to say query. Query, that means is the statement that we're going to use in order just to retrieve the data or information from the table. Okay, so again, select, this means we're going to retrieve the data, insert, and update, and delete. This means we're going to modify, or let's say add a new tuple, or let's say delete. Okay, we are going to cover this one later, more details. Just keeping your mind now. Okay, we do have some query language which allow me to create schema, table, index, constraint, etc. on the database, and another, let's say, language that allow me in order to access and update the data. Okay, we are lucky SQL is going to take care of both of them. It's going to provide, they have parts of the commands allow me to do all the job that I'm looking for. Access the data, modify the data, create the schema, and etc. Okay, you can classify this one into two parts. For example, if you go over this one in more details for the data manipulation language, the first one we call as the pure. The second one is commercial. Pure, that means providing properties about the computational power and for optimization. Mainly, we're going to study one of them. We call this one the relational algebra. And the reason behind this one, if I understand this one, it's easy for me to understand the SQL language. Plus, usually we use the relational algebra when you try to optimize my query. It's similar to any programming language. For example, when you write your code, whatever programming language you're going to perform, you need to compile your code, yeah? When you compile your code, the compiler tries to find what? It tries first to check the syntax of your query, or your command, or your whatever program, right? Or your code. Make sure if there is no syntax error, then if there is an error, it's going to notify you. How the compiler going to do is going to perform something similar, not exact, but similar to the relational algebra. So it's going to first parse the query, or the command that we have, then check whether they have the right syntax or not. For example, if you say select nothing, you don't type anything from instructor. When you send your query like this, the system gonna say, okay, select, oh, something missing. You didn't specify what type of attributes or the list of attributes that you want it to be in one part of the result. So you can discover this one. Okay, so using relational algebra allow me in order to parse the query, and also allow me, we cover this one more details, CS 525, in order to find the best plan in order to execute your query. Okay, the commercial one was the SQL with the most widely used commercial language. So data definition language, data manipulation language, okay? So we can classify the data manipulation language more into two parts. The first one, procedure, and the second one, non-procedure or declarative language. So what's the difference between them? For the procedure manipulation language, you have to tell, okay, or specify what information that you're looking for. For example, I want the list of for example, the ID and the name of each instructor in computer science, okay? So you specify what kind of information or what information you're looking for. Good. And also, you are going to tell the database management system how could you get this information. For example, you have to go there, open that file, perform this operation first, then after that you can display the result. Let me give you a quick example, but we are going to cover this one later in more details. Assume that you want to, let's say, select all the information from the instructor department. So the system here, the procedure, you have to say, you have to access the instruction. Okay, you have to select, for example, the list of, make sure that the department equal computer size. Then you have to just project the list of attributes that I'm looking for. So I give you exactly the steps that you have to perform. Okay, for the non-procedure of declarative language, with the as example going to be the SQL here language. Here I'm going to do what here? I'm going to just tell you that, please, I want just the list of all the instructors that belongs to the computer science department or works in the computer science department. How can we get it? It's your job. Try to find the best way. I'm not going to tell you how. That's why we call this one declarative. More details, hopefully next lecture when we talk about the relational algebra, and once I done cover the relational algebra, so I'm going to go back to this part, okay? Give you more examples, show you why the relational algebra is going to, in this case, you have to tell what do you need, what kind of information. Then at the same time, you have to tell me how, in which order, which step. Maybe this one is not clear because they have only one relation, but if you have two relations, the situation is going to be different. Clear, guys? The other thing, we call this one data control language. Oh, what do we mean by control? Remember, we talk about the difference between the rely on the operating system in order to take care of the job or task that we planning to use database management system we're going to do. That's one thing. Security, remember we said using the database management system you have full control. You can specify, for example, if you have one relation and just keeping using the instructor. Let's say you have student relation, and the student relation you have a student ID, name. Assume we have, for example, social security number. Assume this is part of the information that we're going to store. Just an example, okay? So here, using database management system, you can control who accesses this relation, the whole relation, and who cannot. I can grant and revoke. I can give you like a permission. Who can read? Who can insert? Who can modify this? Who can delete any tuple from this relation? Yeah, that's the grant. Revoke, that means you can remove the permission. For example, maybe I give you access to this relation, then after that I decide, no, I change my mind. I'm going to revoke this one. We're going to cover this one later, but just to keep you in mind here, we have full control about what kind of information is going to be shared, with whom can access what. And here you can specify, for example, fine grain cost, or fine grain, control. You can tell, for example, who access even attributes. You can tell, for example, user 1 and 2 can access ID, student ID, name, or all the information. User 3 can access only the student ID name, but he cannot access the social security number. So you have specified even at the attribute level who can access what. And also, not only access, what you can do here. Maybe I allow you only reading. For some users, I'm allow them to have or perform, let's say, writing, updating, modifying, inserting, deleting, and etc. Okay? We are going to cover this one later, but keeping in mind, you have like a set of control language that allow me in order to control who accesses what and what they can do inside this. Okay? The SQL, perfect. It's gonna allow, they have the command, you can use the grant, revoke, in the way that allow me to have a full control over the data. We are going to cover this one later when we talk about the SQL in more details. The other one, we call this one the transaction control language. Remember the same thing, the first lecture, actually we did this one in the second lecture, when you start talking about if we have a multiple user try to access the data, at the same time, what if we try to execute, let's say, a query or transaction within the data, something happened in the middle. Remember that we try to transfer money from account A to account B, we deduct $100 from account A and we need to add $100 from account B. What if you start deducting money from account A and the system crash? So it's gonna happen here. So here you can specify this one thing. Is not, we have a different ways, but this is just a quick example. You can say, I have a list of commands. or queries, whatever, okay? I want from you to use this one or execute them as one unit. What does that mean? Or atomic. That means either these commands are going to be, all of them is going to be executed or not, none at all. For example, if we have 1, 2, 3, 4 different commands, when we say commands, it might be queries, okay? Select, insert, etc. Okay? Somehow, I need to make sure that all of them must be executed at one unit or together or none at all. So I can tell, for example, or one thing else. Sometimes after you perform set of commands here, maybe here you figure out something wrong here. Maybe divide by 0 or figure out that something wrong. That means I need to undo whatever I did from 1 up to 4. So either you're going to commit, that means whatever these commands from 1 to 4 must be executed, must be reflect the change to the disk, or undo, that means roll back, that means forget it. It looks like ignore whatever I did. Undo whatever I have done. We're going to cover this one later when we talk about the transaction. Okay, that's what you call transaction control language. Lucky us, SQL is going to take care of this one. It has a set of commands, allow me to specify or do this job. Okay, good. The SQL Query language, which again, I'm just put this one separate, but still we can deal with this one and handle this one as a data manipulation language. Okay, is a null procedure. We know that, yeah? That means it's declarative. That means just tell me, for example, what do you need, what information do you need, but we are not gonna tell the database management system how they can get this information. It depends on you. Take your time, do whatever, as long as you give me the result. Okay? Find all the sorts of the computer science department is one example. And generally speaking here, maybe as an input for the SQL query language, maybe you have one relation, maybe two relation, maybe three, maybe number of relations. It's fine. Okay? This is just example. At least we have one relation. Actually, sometimes you don't need those one. But generally speaking, in most cases, we need to extract or modify or apply whatever query based on or using at least one relation in order to get the result that you're looking for. Don't worry about the structure, what do you mean select from where. We're gonna cover this one later in more details, but just doesn't help if just explain to you. Here I want to select the attribute name from which relations, where the department name equals a specific department. And the department name and the name of the fields or attributes stored in this relation, and the instructor, which is going to be the relation that I want to get the information. Okay, sometimes it's not enough to use SQL in order to do your job or build your applications. Assume that you're going to build an application require from, let's say, collect information of the user. For example, web application. In the web application, what do you need to do here? First, I need to collect information for the user. For example, the user, they say ID and the password. Then you can say login. Something like this, okay? How can you build this form using SQL? I can't. This means I'm going to rely on another programming language. Java, Python, whatever you want. Yeah? In order to build this interface to me. Once I collect this information, somehow I need to convert these or the information that I collect in the SQL query. Okay? That's what we mentioned here in this part here. So we need to have what we call the application programs, which allow me in order to access data through one of the language extension. In order to perform this one, we're gonna see later, we're gonna use this one interface. It depends whatever, by the way, what programming language we're gonna use. Psycho, I guess that's for the Python. For the Java, we're gonna use the JDBC. We're gonna cover this one later when I'm gonna talk about the advanced SQL. So I'm gonna give you the way, how can you write application? How can you connect your application in order to translate whatever the commands that we got or information that you collect using the application program into the SQL query, and it's going to be executed in the database at the end. Okay, so just speaking, when you collect this information, somehow I need to use what? Extract SQL commands query. For example, select from the relation or whatever the password, or let's say the file that contains the credential of the user, because every time we try to make sure whether the user allowed to access the system or not, you collect username and password, check in the specific file, see whether this username and password are matched. If they match, you grant access. If not, you say maybe try again or redirect them to another page. Anyway, you need somehow collect information to compute SQL. Then we're going to use the GDBC, for example. If you use the Java, this is going to execute this command in the database. Then the database is going to apply the result. Then after that, you need to maybe, if you're using web application, you have to create a dynamic page, redirect the user on the login page after they successfully log in, or failed page that asks the user to know that you enter the say the entry again or try again. Again, we are going to cover this one in more details just to keep your mind. Sometimes we cannot rely only the SQL language in order to do our application or create your web application or whatever, or desktop application, because we cannot do everything here. Yeah, forms, mainly forms, collect information of the user, and also when you display the result as, let's say, a report, or let's say display the result in a nice way or user interface. Yeah, so we have to rely in one specific application program. Again, we are going to cover this one in the chapter 4, 5, 6. That's what we talk about here. Okay. The question here: how can you design my database? The process of designing database or general structure of database, you can follow two main steps here. The first one, the logical design. Before you start talk about the database here, you need to collect information. You need to talk to the domain expert. Yeah. For example, someone hire you in order to build database application. So first, don't start writing your query and the relation. No, you need to understand what they're doing in the real world. And that's what we simulate. I'm going to give you the class project, okay? The class project looks like you're talking to the domain expert. I'm going to show you or give you the requirement. What do I need the system that I hire you to build looks like, or what kind of functionality, what kind of attributes. That's what we call the business decision, okay? For example, maybe they said, okay, we need to keep tracking or have information about, for example, let's say it's your university database. Someone hire you to build the university database. First, you have to design this one first. When you design, this means you have to tell what relation do we have, what tables, what attributes, yeah, how to build them. So collect information. University database require from you to collect information about the student, instructor, department. Okay, you said the student, instructor, department. Okay, what kind of attributes? You said for the student, we need to have like student ID. And generally speaking, the student ID starts with the letter A. And let's say, just for example, okay, 9 digits, for example. Maybe it's not the right one, but for example, okay, let's say 1 letter, then 9 digits. Okay, we need to keep let's say tracking for the student name. Generally speaking, student name, we have first name, middle name, last name, or put them in one attribute. Then we need to have, for example, the phone number. Maybe the students have more than one phone number, etc. So you collect this information, all of them. Then now it's gonna come to what is called the computer science decision. You are the one is gonna decide, okay, it looks like I'm gonna have maybe 5, 6 tables. Okay, and you are going to distribute the attribute among these tables. They are not going to tell you, for example, you have to create a student table that contains this information. They just give you the information, then you are going to decide how you are going to organize them. We are going to cover this one later in more details, okay, when you talk about the, let's say, entity relational model. I'm going to show you how can you do that, okay? Then after that, once you define or design or come up with the structure that we have, then you need to take a look how you are going to store them in the disk. Okay? What data structure you're going to use, we try to touch them in the end of the semester, show you how you can control the way that you're going to store your data in the disk. Okay? One thing is sometimes you end up we have like an not perfect design or bad design. Something weird in your design. For example, let's give you this instance of the relation. So what this contains information about what the ID, name, and salary looks like: instructor ID, instructor name, salary, department name, building, and budget. What do you think about this design? What this instance did here? What I did here, I create one relation that contains instructor ID, name, salary, and the department name, and the building, and the budget. So what did you notice here? What do you think is good design or bad design first? bad design. Why?
I think building and budget shouldn't be there if you're using individual persons and their salaries in the department.
Exactly. So it looks
So
like
I
we
don't
have
think that matters.
unrelated information, and at the same time we have redundancy. Yeah. Take a look. Redundancy of the data. Assume that. So it looks like this one. All I need, maybe I need only the department name. I need just to keep tracking. For example, this guy or this instructor works in that department. Do you need the building and budget? Maybe this information is going to be in separate table. That's one thing. We're going to show you later how you can take a look to your design, how you test whether your design is good or bad. One more thing here. Assume that, take a look to the one that works in the computer science department. This information, they're the same. So it's going to be the building and the budget going to be the same. Yeah. So I'm going to repeat this information over and over. Someone has said, okay, I don't care, it's not much information, but remember, what if you have a large amount of data? This is what you call, maybe cause some anomalies in the data. What if you try to modify, let's say, the budget of specific department? For example, the computer science, they said 100,000, maybe 900,000, for example.
This table needs to be normalized.
Sorry?
Table needs to be normalized, completely normalized.
Exactly. We're going to cover this one later about what do you mean normalization and denormalization. But just to show you that sometimes you end up with the bad design, then you need to figure out, we're going to see how can we test my relations and how can, for example, what is called, here in this case, how can we fix it? Okay?
So, I have a question. So clearly that we can split into many tables, and that way we can save space, okay? And more correlated to the actual logic. But is there actually a benefit in terms of simplicity for storing the data just like this?
For the simplicity is okay, but we have redundancy of the data. That's why I'm trying to say what might cause what's called anomalies. For example, when you try to modify one data here, you need to make sure that, for example, the budget for specific department, you need to scan the entire table and make sure that the system, there is no cache, and you manage to update all of them. That's one thing, okay. The other thing here, for example, what if I need to keep or add in department that doesn't contain, or there is, for example, new department. How could you insert this information? The department doesn't have any instructor yet. New department. So in this case, you have, for example, department XYZ, building A, budget 1,000 or 10,000, yeah? So what's going to happen here? There is no instructor belongs to this department yet. So this one's going to do what? Blank? No? Did you see what's the problem right now?
You're not going to write it. It's not going to be existent still.
Yeah, so what I have to do here in this case? I use null value. That's one problem, yeah? But we have a problem here. We have the instructor ID, it's going to be null value. Later, when you're going to talk about the key, when you use the key and the ID is going to be the primary key, is not allowed to be null value. So we have many problems here. This is the simple problem. Or maybe we have a new instructor that doesn't belong to any department yet. So in this case, we will follow information here, and then here, null, 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 because it doesn't belong in any department. We don't like we have this instruction. And it's going to violate some constraint, integrity constraint. Okay? More when you talk about, after we design our data, when I'm starting to talk about the normalization, I'm going to come up with this example again and go over what's the problem here. I agree with you. Maybe someone will say, for simplicity, yeah, maybe put all the information in one table. That's perfect. Generally speaking, people at the beginning when you design a database, put everything, all the information in one big table. Because it's easy, but it's going to be a redundancy here. And maybe you have some anomalies when you try to insert, delete, modify. Yeah, by the way, what if I want to delete a department or instructor and assume this instructor the only instructor in the specific department? So I'm going to lose all the information related to this department. And the vice versa, the same thing. If you delete the information related to a specific department, in this case, it's going to delete all the associated instructor in this department. You're going to lose information about the instructor. So you see that it's not good design. More, we're going to talk about this when we cover the normalization. Clear?
Yes.
Good. It's yes or yes? Because there's a yes and okay. I'm just kidding, by the way.
Yes, okay.
Okay, yeah. So the second part here, so next one here, give me a second here. Yep. So that just summarize what we talk about. So just speaking, when you design a parse, we're gonna take a look in two ways, mainly two ways. Okay. The first one, we're gonna take a look at the entity relational model. And in this case, which the one that I'm gonna start talking about this one before the SQL, because if you finish the entity relational model, so you're gonna be able to finish phase 1 and phase 2 for the class project. Okay? Anyway, so in this case, you need to take a look at the data that we have. Then you are going to decide how could you, for example, organize or distribute the attributes, what kind of relations might you have, what kind of entity sets, etc. So we're going to talk about the entity set, relationship, and the relationship set. Okay? So here you end up, we have like a tables, relations, and each of them has its own attributes. Okay? So in almost, if we follow the exact instruction, you're gonna end up in the most of the case, maybe 95 or 98% that you have a great or good design. So maybe you didn't need to perform the normalization. With the normalization, we're gonna cover this one at chapter 7. It's gonna be after you talk about the SQL. And this case, you can tell after you finish your design, it doesn't hurt. If you take a look to your design and said, okay, you can decide or specify whether this design is good design or not. If this is bad design, then you can say, for example, use a normalization. That means you have, for example, if you find one table, the same thing, let's go back here. If you figure out, for example, this table is bad, so that means maybe you can do what? You can split this one into two tables. That's what's called normalization. You start on one table, there's a set of rules. If you can, by using these rules, prove that design is bad, that means you need to split this one. That means you put too much information in one table, that means we need to split this information into two relations. And you're going to continue doing this operation over and over until you end up to have a good design. Of course, we have a set of rules, we have a normalization form. That means we can specify what requirement, what's your definition for good design, and you need to make sure that all the relations satisfy whatever normal form that you're looking for. Okay? We're going to cover this one in chapter 7 later. The other thing that I think I was planning to finish this one. Okay, let's do this one fast. Database, generally speaking, is what? A set of softwares, different models. So we don't have only one component and put everything in one component. No, we have a different components, different software, okay? The first one, storage manager, which is going to take care of the way that how to store your data on the disk. Okay, then after that, remember, as a computer science, everything going to be stored in the disk. Yeah, when you try to execute, manipulate, modify, access, delete, whatever, process data stored in the disk, you have to fetch this one into the memory. So the storage manager is going to take this one. It's going to store the data in the disk, organize, take care, the way that depends on what file organization going to use in order to store our data, and also going to be take care or be responsible, fetch the data back and forth from the disk to the memory and back to the memory. Okay, the other thing we call this one the query processor. Okay, which do what? This guy is going to be responsible for the processing query. That means when you send your query, for example, select a star from the data, the system is going to do what? It's going to go through over many steps. The first one, do the parsing. Okay, the similar to the compiler class. If you study compiler class, it's similar, but not the exact operation. It's going to parse, take a look to the structure, to the query, make sure that your query is syntaxed correctly. For example, you have a select something from, that means, okay, you have a select and specify the list of attributes that you want. If you don't, the system gonna say, there's a problem here. Yeah, you're missing a semicolon, you have wrong operation, and etc. Operator, the system can discover this one. Then, after that, the system or the database management system gonna do what? It's gonna go over, for example, different plans. What's the best plan or the best way or the fastest way? Or the cheapest. When they say cheapest, doesn't mean the cheapest one for the money. No, for the cost. In the speed. Which is the fastest one we can use in order to execute this query. So you're gonna perform this one, come up with different plans, then the system gonna say, oh, this is the best plan that you're gonna perform. Then after that, it's going to execute this one, then after that, you perform the result. The other components, we call this one the transaction management components, which in this case take care of the way that we have multiple users trying to access the database for the concurrency control and also recovery management. That means, remember, we talked about this one in the second lecture, where I've said, for example, sometimes when you perform your query or command, something bad happened in the middle. The system is going to be cached. So how could you recover? How could you recover to the most recent stable state or the previous state before the failure happened or occurred or before the crash? Okay, then gonna be take care of this one. We cover this one in more details in CS 525. So, but it doesn't hurt to keep in mind there's many components in the database and how it looks like. Okay, this is just the diagram. Just summarize what to talk about here. This is a disk storage. This is a storage manager. Whatever the data you see, the data how did it be stored somehow. Then every time you need to fetch the data, the storage manager is going to be responsible. Of course, it's going to communicate with the operating system and they're going to say, I want this block, fetch this one to the buffer. You are familiar with the virtual memory. It's similar in this case. Everything you need to put in the virtual memory. So if it's not available there, then I need to fetch this one. We're going to do this with something similar in the buffer manager. Okay? I don't need to go over this one in more details. I already summarized this one. This is just more details. Yeah, we have one component in the storage manager we call authorization and integrity manager. For example, when someone, as a user or application, send a query, the system needs to make sure that whether you are allowed or whether you have the right access right or whether allowed to access or perform this operation or not. Remember we said we have a grant, we can give you access right or permission, what we can do in this relation. If you don't have the right access right, then you are not going to perform this operation. Yeah, go ahead. Okay, I thought you talked to me. This is what I've said about the, by the way, this is going to be chapter 12, 13, or 14. As I mentioned, if we have time, we are going to cover this one. Take a look, at least give you an idea how it works. If not, then I will upload the slides to the Blackboard, so you're going to be able to at least to take a look at this one. This is the query processing that I've said. You have a query processing, try to find the best way, optimizing, come up with a plan, then it's going to execute it, then it's going to give you the result. This is going to be covered of chapter 15 and 16. This is a transaction manager or management. When it's a transaction, generally speaking, we talk about the collection of operations, set of operations. You want to execute as a one unit mainly. Okay? Database architecture here, just, we just take a quick look at what the architecture of the application that use the database as their backend. Okay, this is one here, yeah. So we do have what's called the two-tier architecture or the three-tier. The old one used to be the two-tier. What does that mean here? When you build your application, the top of your database, web application, desktop application. In early days, this is not the modern way to write your application. We used to have what? We have this user, yeah, and your application gonna be here. So here, your application, you're gonna write your application in the user client side. And when this application tries to communicate with the database, here through the network, you're gonna send the SQL query. And here, the database server or the database systems will interact with the database, then the database is gonna reply with the SQL here. So I'm going to write my application, it's going to be at the client side. This is a bad idea because if you send your SQL directly, someone can interrupt this one, it's not secure, it's not efficient, and at the same time, in this case, maybe someone going to modify this SQL query. The second one, which is the one that we used, even this class, the three-tier application architecture. So in this case, what's going to happen here? So it looks like we have this is the client. Let me write this one here, it's already here, yeah. So this is the user. This is the client side. I'm going to have an application client. This one is going to do what? Collect the information, whatever. Assume that it's going to be web browser. You're a web browser. You try to log into the Blackboard or check your email. So here web browser is going to collect this information and send this information to the application server. The application server, if you're looking for, let's say, a static page, it's going to apply with the static page. If you're looking, for example, try to log into your email, this means it's going to be dynamic page there. So this application server is going to collect the information that you have here, then send SQL queries. This is going to be at the server side. You see, that's why it's secure to the database system. The database system is going to say, okay, this is the result of the SQL query. Then the application server is going to build the dynamic page. Let's see here. Then now send you the HTML or whatever page is going to send it to you. This is more secure because here we can use whatever secure connection. And here I'm not going to exchange or send the SQL query. And we're going to see later when you talk about the advanced SQL, I'm going to show you the way how to make sure that no one can perform what's called SQL injection or try to modify this request that you send to the server. Okay? What are the different users that we can use in the system of the database? Just speaking, we have the normal user, or naive user, the one that we have, for example, we have application programmers, the one that build applications. I'm not going to say we are the naive, let's say we are normal user. So in this case, you are not directly interact with the database itself. So you are, when you log in to check your email or go to the Blackboard, you are not write SQL query. You have web browser, communicate, there's someone write application to you, so just you use the application interface. That's the normal user. There is another user. So this one just use. The other one, we call this one the application programs. This one, the one is going to create the application. The one that the IT hired in order to build whatever the system that we use. The IT portal or whatever. Okay? There is another type of the user. We call this one sophisticated user. These guys can interact directly with the database. So these guys can write SQL query directly to the data, or access the database, either using specific tool, analytical tool, etc. So they are not going to use the application interface. When you try to log into the database, they are not going to use the web browser or whatever. Okay? We do have another user who is the one, very strong one, very important. We call this one the database administrator. The one that do what? Who's going to create, for example, when you build your design, the logical level, now we have, for example, let's say a student, university, we do have a student instructor, student advised instructor, we have a courses, etc. We have that relation. Now, then we have the schema of the database. Yeah. Now we need to find out how can we create this one in the database. Who's gonna create these tables and the schema, let's say the integrity constraint of the index on this database, the database administrator. So it's gonna use the data definition language. Okay. Of course, this interpreter, that means I'm not gonna go over this one more details, but when he send create table and the name of the table command, the system say use this component in order to check whether it's correct one. If correct, it's gonna create a database. Okay. Also, they can grant the user access, modification, etc. So you can use the data manipulation language. I remember that I classified this one 4 different components, but I've said at the beginning, mainly we have 2 language or query language we can use here, or database language. The data manipulation language, data definition language. So maybe you can specify who can access what, and etc. And also you can fill the data. Yeah, insert, modify, and delete. You can do this one, but mainly this can be done by the application program and application interface. For example, you can allow, if the system allow you to register as a new user, and etc. Okay. So the data administrator, just go over this one more details. The one has full control over the system. You can create a schema or define the schema. Define the schema. When you say create a schema, this means you're going to use the data definition language command create or alter. Okay. Take care, for example, how this is going to be stored at the lower level. You can modify, you can manipulate that. You can grant or revoke the access right for the users. And also sometimes, or most of the cases, it's going to perform the routine maintenance. A check backup up with the database, because one way, in order to keep our data running, we need to perform what's called the backup. Whatever I have data stored there, I need to make sure that I have a backup plan or store this data somewhere else in case the server crash or someone stole the hard disk, etc. Still have being able way in order to continue serving the user or the customer. Make sure there's enough space. Monitor the job running in the database, because sometimes you see some multiple user maybe you do like malicious query that maybe prevent other users from using the database. or try to harden the system. So you can monitor it here. Okay. Make sure the user don't do very expensive tasks or in order to harden the system, and at least you see who accesses what. This is the most important thing. Like audit, you can use this one later in order to figure out what happened in your system. And etc. There's many tasks, but this is, I mean, the main task is going to be performed by the database administrator. History of the database systems. I hate this slide because the simple thing I'm going to say, started in the 1950s, they start working with the database. Then we end up in 2000 maybe, or 2010. I'm keeping saying this one, database gets evolving. We are starting in 2000, we take a look at the database of storage, which has big database systems, big database analysis. Then after that, starting in 2010, people get back to the SQL because still SQL is one of the important query language we can use in order to retrieve or modify the data. Okay, so this is the end of the chapter 1. Okay, so what do I like to do the next? I think we still have time, so I'm going to take a look to the second part with the relational data model. I'm going to give you more details about the relational data model, what the goal that we try to achieve, how it looks like, then go deeper in the structure. When you say table, what do you mean the table or the relation? When you say schema, what do you mean exactly by the schema under the data model? Okay, or relational data model. Then after that, we're going to take a look at the formal relational language. Usually we used to, or they take a look at the textbook. Some textbooks are going to use SQL first. Then after that, so I mean, they cover the SQL language before the database design. So I prefer to start with the relational Java. Then I'm going to give you the database design first, use an ER model, because I believe you need to understand how you design your database from scratch. And also, you can start early working with your project. Okay, phase 1 or phase 2. Then after that, we take a look at the SQL. In the SQL, I'm going to divide this one in 3 parts. The introduction of the SQL, then intermediate part, then the advanced. The advanced SQL, I'm going to work mainly in the SQL more details, how to write your program using Java code. And they give you like example using the Python. Yeah. But mainly I'm going to rely on the Java. So it depends on you. I'm going to give you the codes, how to access the database using the Java and Python, but mainly I'm going to focus on the Java, okay? Your choice, whatever programming language that we're going to use in order to build your application and the class project, it depends on you, it depends on group member, whatever programming language we're going to decide to work with, whether you're going to decide to work with the desktop application or the web application. I'm going to try to cover this one in this part. Let's say after you finish the advanced SQL, give you maybe 1 lecture just how to build your web application. Okay. Then back to the after you finish the ER model or SQL, I'm gonna back to the normalizations here. Yeah. Then if you have a time, I guess maybe have 1 or more lecture. We can cover the transaction processing, recovery, concurrency control, storage of file, how the data is going to be. So it looks like you're going to go to the low level. Yeah, I'm going to take a look how the database or data is going to be stored in the database, in the disk. Yeah. By the way, we are talking about the disk operate, let's say database management system. We do have another database with in-memory database system. I'm not going to cover this one here. Then I'm going to cover the indexing and hashing with a different structure. How can we access or find out better way in order to access the data? Then hopefully query processing and optimization. Definitely, I'm not going to have a time to cover this one in more details. But generally speaking, CS 5 to 5, we cover these parts in more details. Okay, so that's all for the chapter 1. And let's take a look at the chapter 2 again. Any questions, by the way? I'm trying to speak slow, okay? Slow. If I speak faster, please stop me at any time. Okay. So the part 2 here, I'm going to introduce to the relational model here. This is chapter 2 if you have a 7th edition of the textbook. This is chapter 2. Or if you have used the 6th edition, both of them actually available online. I guess you can check the the 7th edition is available. Hopefully you Google it and find it. Anyway, with the 6th edition, it's going to be chapter 2 and 6. Okay? So what I'm planning to do here? In this chapter, we are going to study the fundamentals of the relational model. I'm keeping saying the relational model, relational database, etc. Let's take a look at more details. What do you mean by exactly this component? How the table looks like, what the components stored in the table, and after that, I'm gonna talk about how can we, or the structure of the data model that we end up, how to create a schema. Then after that, talk about the keys. What do you mean? Introduce you to the notion of the key, why you need the key, what do you mean by the key, talk about the integrity constraint with more details. Then we're gonna stop here and talking about the second part with the relational query language. More details, I'm gonna take a look at the relational algebra. Again, if you understand the relational algebra here, that means you don't have a problem using or understanding the SQL. Okay? We talk about the relational model. We said that the relational model introduced, I think, 1970, 1965, I'm not sure with the date, anyway, with the TID code. Yeah, remember the guy that you talked about last lecture? We said he notes that people, or the people working in the database field, keeping rewriting their code over and over every time, or spend long time just to rewrite the code because there is a tight coupling between what's called the physical and the logical layers. Yeah, the structure that you the database, and also how the database is going to be stored in the disk. We covered this one before. Then he came up with an idea with the relational model, with the change the way that how the data is going to be designed and works, and come up or end up with what is called the clear separation between the physical and the logical model. Okay? Anyway, so I'm going to go over what he said with more details, okay? So the relational data model defines three concepts. Mainly it has three concepts, okay? It's going to define first the structure. When you say, what do you mean the structure? Then after that, the integrity. Then after that, the manipulation. Let's go over this step one by one. And we are going to cover or go over the more details during this lecture. I mean, this chapter, not this lecture. We have only 5 minutes, so I'm not going to have enough time to cover all of them. Anyway, so it's going to define the structure. When you say the structure of the data, that means is what? What we mean by the structure is the definition or of each relation that we have and its component. So you can tell, for example, how many relations do you have? 5. What's the name of each relation? This relation 1, 2, 3, 4. What's the content? What's the attributes going to be stored in this relation, and also what's the value that's stored for each attribute in this relation. Anyway, assume that we have instructor, or let's say I have a student. I have a relation called student. So for the structure, it has to specify what the student, what its contents. For example, it's going to be student ID, name, and GPA, just for simplest. Then you have to specify here the possible values these attributes can hold, or the domain. For example, in the ID, it's going to be, for example, string. We are not going to use a string, but assume that we're going to use a string here. Okay, what's the data type? And you can specify the ID. It's going to be, for example, must contains, to say, character A, then a letter A, then a list of, for example, 5 or 6 or 7 or 9 digits. Yeah. Name. For example, you can say the name is going to be string. The GPA is going to say, for example, float, or let's say double. Of course, we're going to use different data types. When we talk about the database, we're going to cover this one later, but just assume that the assumption, that's what do you mean by the domain. What the possible value for each attribute. So the GPA is going to be double. What the possible value will be between 0, up to 4.00. Okay, this is the lower value and the upper value. The string, you can say this maybe have, for example, 30 strings, the size 30 character can be stored here. And here maybe you can say 10 characters. And must start with the letter A. Yeah? Something like this. Clear? That's the structure. The second one of this, then after that is going to define what is called the integrity. When you talk about the integrity here, what do you mean exactly here? It's like the constraints or the rules or that I want to impose, okay? Or I can enforce in each tuple. For example, you can specify for the GPA must specify this value. For the string, it's not allowed, or let's say for the ID, it's not allowed to have the ID start with letter B. something like this. Yeah, you have a set of constraints. Oh, the salary must be greater than 0, or the budget must be positive value. So these kind of constraints that you can enforce. Or you are not allowed to have blank ID when you store information in the specific tuple. So it looks like you have a set of rules. It depends, of course, on the domain that you need to implement. It depends on the description that you get with the domain expert. You can tell you, for example, what kind of value, what kind of we expect to store with each attribute, and also what's the allowed or disallowed value or illegal values. So those are the set of rules. We are going to cover this one more details, but just keep in your mind, in the relational model, first, we're going to perform, or need to create or define the structure with the relations and the content. And when you say the content, it means the list of attributes and the values that these attributes can hold, or sometimes we call this one the domains, with the possible legal value for these attributes, each attribute. Integrity is a set of rules that you need to enforce, that must be satisfied by every single tuple or data or instance of this relation. Okay? Then after that, the third concept that we need to define here, or the relational model define, is going to define the manipulation. What do you mean by manipulation? It's clearly that I'm talking about the ways that how can we manipulate the data, the ways that how can we access the data, and also the ways that how can you modify the data. I'm talking about the access, select, insert, update, delete, and etc. Yeah, how can you manipulate the data? So those are the three concepts, okay, that define, concept that be defined by the relational model. Okay, so we are going to try to go over them one at a time, starting next section with more details. For example, I'll show you the structure, then how can you enforce the integrity. You need to define the notion of the key in general. Then I'm gonna say how can you manipulate the data, which I'm gonna give you example, how can you use the relational algebra in order to manipulate the data or access the data. Okay, so now go more details. So we said the data is gonna be represented as a table. Okay, so what's the structure of the table? When you talk about the table, that means we have something like this. We have a tuple, or maybe you can see rows, which is this one, and we have a columns. Yeah, that's the table. So you have to specify, like you have a set of, let's say, each relation is gonna have unique name. For example, you cannot say I do have in my database two relations and their name are the same. So in this case, we don't have something like this. If you said, for example, you have a relation R for simplicity in the database, that means you cannot have another relation has the same name. So the name of the relation must be unique. Okay? And the relation is gonna contain what? A set of attributes with a column and the set of, let's say, tuples or row. So the column or attribute, or let's say fields, we have different names we use. Okay? All of them, as I need to just to specify the way in order to represent a data type that's going to be stored in this table. So the type data entry, okay, present in each tuple in the relations. So let me go here, jump to this slide, then I will get back. You see that we have those are the fields. Unique name, we don't have, for example, we cannot have like another two columns that have the same name. The same name must be unique, which is going to represent data type that I want to store in this field. From where I got these names, of course, it depends on the database design of the domain that you try to implement. Okay, you are going to specify what the set of attributes is going to be stored in this relation. Okay. Then here we have what is called, the row or the tuple. Okay, which is going to be the single entry. This assume that we have this one as example. This one row or one tuple, okay, with a set of entry, or the single entry, sorry, in the table, having what the attributes specified by the schema. So from where I got this set of attributes must be defined in the schema. For every single relation, I'm going to define a set of attribute fields that's going to be stored in this relation. In other words, I'm going to describe, yeah. That's one thing when we mentioned the schema before. We define the schema as the way in order to capture and describe the structure of the data. So the schema of this relation is gonna have like ID, then whatever the data type that you wanna use, for example, whatever, let's say, how could you represent the data on the disk? Either it's gonna be integer, either it's gonna be chart, string, double, whatever. Then the second attribute, which is gonna be name, and you have to specify what the data type and etc. Okay, and assume this relation is going to contain information about the instructor, so I call this one instructor. Okay, we do have two, let's say, terminology. The first one, we call this one the cardinality. The cardinality, that means the number of tuples in this relation. Which equal the number of tuples. So the cardinality in this case, we do have 12 unique tuples here. And we have another terminology, we call this one the RT, or the degree, which equal the number of what? Of the attributes. So in this case, we have 1, 2, 3, 4 attributes. Okay? One thing I need to emphasize here, the relational table must be a multi-set of tuples, which having the attributes specified by the scheme. Clear? That is the structure of the relation. We say I'm going to store the data or represent the data or describe, organize the data as, let's say, relation or table. This is the way how it looks like. Multi-set. This is, I mean, the tuples that we have. Okay, so let me go there. That's the definition here. We define a relational table with a multi-set of tuples having the attributes to specify the schema. The attributes of the column is going to be the type data entry. I mean, present in each tuple in the relations. Okay? And the single tuple is going to what? Is like a single entry in the table. For example, you have a table that captures information about the student. So in this case, for every single tuple is going to represent data that belongs to a specific student. If you have, for example, 100 students in the class, then in this case, you're going to have like 100 students going to be, or 100 entry in this table. Okay? One thing I need to add about the attribute itself. Each attribute we said is going to have a name. I need to specify must unique name. So that means you cannot have two attributes in the same relation that's going to have the same name. No way. The set of allowed value for each attribute is called the domain. Yeah? What does it mean, the domain? You know that for every single entry, you can specify a domain, which what the set of allowed value can this attribute have. For example, you can say, I'm going to define, say, x as integer, and integer maybe it's going to be from 0 up to 100, which is the domain. You can specify what the domain, what the set of valid entry or value for this attribute. The department name, for example, as I mentioned last time, assume that we have only, let's say, 2 departments in our university. So the valid entry of this domain is going to be computer science, for example, and math. Nothing else. Yeah, that's what you call the domain. You can specify the set of domain for the integer, any integer number. You can specify, for example, if you define your data or the attribute that you have as a string, you can specify, you know how to define a string, yeah? What's the valid entry of the string? Any combination of the digits with the character, yeah? With a special character, all of them is going to be fine, as long as between double quotation. That's the way how to define this one in the programming language. Okay? There is one exception here. The attribute's value required to be atomic. What does that mean here? That means it's indivisible. In this case, if you have like, let's say, phone number, can it create an attribute that holds the phone number of the student? Yes. Here in the phone number, you must have only one phone number to store the data. That's why you call this one atomic. So what if you try to store, let's say, more than one phone number for the student? So in this case, you have the first phone number, let's say, the first one, then you have 2 phone numbers, yeah? In this case, based on the initial description of the relational model, you cannot do that. The value must be unique that you want to store within the attribute, or must be atomic, cannot be divided further. Later, when you talk about the database, the design, etc., we are going to relax this, constraint. But right now, when you talk about the relational data model, the original description of the relational data model, they said the data must be atomic, or the value that's going to be stored within the attribute must be atomic. If you have more than 2 value or set, you cannot store this information. We are going to deal with this one later, as I mentioned when you talk about the database and the SQL, etc., we are going to relax this exception or this integrity. For example, if you have the data is going to contain names, for example, and in the name, generally speaking, you construct the data or the value is going to be has 3 parts: the last name, middle name, and first name. Here, based on the definition of the relational data model, you cannot do that. You have to break down the name into 3 parts in order to be able to store the data, because the data is not, or the value is not atomic. Because last name, middle name, first name, I can divide this one into 3 parts. So this one, in order to store that using the relational data model, we have to say, for example, first name equal the value, the other attribute last name, and maybe I have middle name. So this one must be stored as, to say, 3 separate attributes. Clear, guys? There is another thing we need to add to the domain. Okay, we call this one the null value. How can we indicate that whether the value is unknown or not exist? Sometimes when you build your data, you try to store the information, you don't have all the information available. For example, you have a new student that's going to attend to this university. Okay, this student just registered, just enrolled, but you didn't specify, or the student didn't specify, for example, what the field or specialist or department wanted to get, to study on. So in this case, maybe I don't know the value, so I need to keep the value blank. We don't keep the value blank. We're going to use the null value with a special value. We call this one null. So for every single domain, we do have a valid entry is called null. Of course, later when we talk about the integrity constraint, you can remove this one. You can specify or tell this attribute cannot have a null value. Okay, you can have some restriction, but right now we have like special value. We call this one null, can be exist for every single domain, which can tell whether capture, for example, the fact that the value is unknown, or let's say doesn't exist. The null value you're gonna see later is gonna cause some troubles, but we're gonna see how can we fix them. Before you try to extract information, you're going to see this one maybe when you talk about the SQL, you see that the null value may cause some troubles, but we're going to take care of this one later. Okay? But keep in your mind, we have a domain which is going to set of allowed values for each attribute, and we do it for every single domain is going to have like a valid value called null in order to identify the values unknown or doesn't exist. And again, this is, the instance of the relation, yeah, which is gonna capture the status of the current state of the data. Okay. How about the order here? Does the order matter? No. The relational data model doesn't mention anything about the order. We said we don't care about the order. Of course, if you want to sort your data when you extract information, then I'm gonna say I want to order the data based on the student ID and name. That's a different story. That's the outcome. But here, in the relational data model, we don't care about the order. And the order doesn't matter. I'm going to have the same relation, the same data. Okay? For example, I've said, give me all the list of the instructions that in the computer science department. It's going to give me this, for example, let me see, this one. I'm going to use this error, and this one. Do you have another one? Yeah, we have 3 instructors. So we have 1, 2, 3 records here. Does the order matter? Doesn't matter, unless if you want the order in your report. But for the relational data model, doesn't care about whether data sorted or not. That's why they say the order of tuples is irrelevant. So every time, sometimes you're gonna store or extract the information, maybe you're gonna have a different order, unless you are going to enforce the order. We're gonna talk about this one later. Back to the schema and the instance, more details. So the schema is going to capture and describe the structure of the data. Okay, so it looks like when you write your code, okay, it depends whatever programming language you're going to use. You have to, once you decide whatever programming language you use, now you're starting to find a way how can we create or define or declare your variables that you're going to use. The same thing here. For every single data model that we have, it's going to have a way how allow us in order to capture or describe the structure of the data. Here for the relational data model, we're going to use a schema, and the schema is going to help us, it's going to be written as the following, actually for every single data model. For example, relation R, you have to specify, let's say, the attribute or list out attribute 1, then you have column here, say the data type of this attribute, and for the rest. So anyone take a look, okay, this is the relation name and this is the set of attributes, then those are the data types. The data type is very important for us because we're going to see later when you try to extract the data from whatever relation that you have a database, you need to have access to the schema. Without schema, you cannot answer the query. And the schema is going to tell me, for example, the set of attributes that belongs to which relations. So now I'm going to tell, when you try to access the data or answer my query, whether I need to access only one relation or more than one relation. It's going to be more details when you talk about the second part of today's lecture, when you try to cover the database language. How can we manipulate the data or access the data? Okay? And also the data type is very important for, at least for the queries part. It's going to tell me, for example, what kind of operation we can perform. If it's string, for example, you know how can we convert to strings, for example. If integer, you know how to compare to integer. Or maybe you can multiply or perform some operation, and etc. Of course, in the lower level, this is going to show me how can we actually store the data on disk. Okay, because you need to reserve space, bytes, based on the whatever data types that we're going to use. For example, integer, maybe you're going to have 32 bits or 64 bits, and etc. Okay? It's a time independent. That means we rarely change this one. Once you design your database, most of the time you are not going to change this one. Unless the university is going to change a lot of stuff. For example, maybe going to say, now we need to add a COVID-19 test. It's going to be part of the data that's stored on the student database. Now I need to add a new column. So it looks like I need to modify, let's say, the structure of the data. But most of the times we are not. We rarely change, the structure of the schema of the database. Of course, it depends on the design. If you have good design, then in this case we rarely this one. If you have a bad design, that means we're going to keep this one, changing the data. Okay? When it does, we need to do what's called reorganize. We covered this one in CS 5.5. Generally speaking, when the data, for example, you either study operating system or not, the data in the lower level is going to be stored on the disk, okay? And the disk, I'm going to use pages or blocks. Assume that the relation R is going to be stored in the block 1 and the block 2 and the block 3, okay? Then, now you need to organize the data. When you modify the structure, maybe the structure, you delete some attributes. So this means the size of the record is going to be less. Assume that this relation R is going to have, let's say, 9 tuples. So for each block, you're going to store 3 tuples, okay? When you reduce the size of the each record, or tuple, or the relation itself, so by eliminating, for example, a few attributes, so the size of each tuple is going to be less. Instead, you have, for example, 100 bytes, it's going to be maybe 50 bytes. So maybe instead you store 3, maybe you are going to be able to store maybe 5, for example. Then here, the rest is going to be 4. Yeah. So I need to do what? I need to reorganize the data. That means you have to reorganize the tuple among the blocks. Then instead of using 3 blocks, it's going to maybe use 2 blocks, etc. And when you try to build your index, we're going to cover this one later, the index is going to keep tracking where the data is going to be stored, for the tuple itself. If the tuple that used to be pointing here now change the location of the other block, I need to rebuild the index in order to make sure that I have right access to which block when I retrieve the data. Just keep in your mind, that's what you call the data reorganize. And used to formulate the queries. You're gonna notice that starting from the first homework, when you give you after we finish the relational algebra, maybe hopefully by the end of this week, you see that I'm gonna give you like the schema. Based on the schema, you can answer the query. If I don't give you the schema, you have 0 chance to answer any query because you don't know the structure of the data. Okay? Instance, which captures the current state of the data. The schema is going to describe the structure of the data, the current state, the content. Remember we said, we have a relation R, for example, it has attribute A, B, C. This is going to be stored in the table. What's the current value stored here? That's what is called the instance of the data. Okay? What's the current value for every single attribute that's stored with every single tuple that we have in the data. It's time dependent because we assume the data is going to be dynamic because we modify the data. If your data is static, then it's not going to change. Okay? It's going to be changed with update transaction, or you say manipulate the data. Yeah, that means in this case, when you try, for example, insert, delete, modify specific value attribute. So maybe the content here for C, instead we have 5, it's going to be modified to 6. So the instance is going to be changed in this case. Okay, and used to evaluate the queries. So I'm going to take a look at the schema in order, once I start building my query, and the data, or the result of this query is going to be evaluated based on the instance that we have. For example, if I said I want a list of all the, say, instructor that works in the computer science department. So you're going to write your query, and when you write your query, you're going to take a look at the schema in order to tell which relation you need to access, yeah, and what kind of attribute you need to extract. Okay, then when you start evaluate this query based on the schema, the instance, or the stored there. So based on the content, the current content of the data stored there, I'm gonna give you the result. So for example, in this case, we do have 3 professors, for example, belongs to the computer science department. So result is gonna be 1, 2, 3 records. If the data, we have only 1 instructor in computer science, is gonna have only 1 record. So again, the evaluation is gonna be based on the instance, based on the current data stored in the database at the time that we run this query. Okay? Good. So in order to try, for example, to come up with, say, formulate whatever we cover, the thing that we cover in general, we assume that we have a list of attributes from A1 to AN, which they say student ID, name, etc. And we have a relation R. This is one way to write the schema. Okay? Relation name, the attributes, the list of attributes without the data types. We can use both of them, okay? This is a simple version. I'm just list the list of attributes, okay? But of course, if you want to be more precise, you need to just add for every single attribute, for example, A1, what's the data type of A1? Then A2, what's the data type of A2, and etc. Okay? So this is the schema of this relation, for example. Let me go back to the slides. So what's the schema here? The schema is gonna be, you have to start with the name of the relation. Then you have to list all the attributes. And for every single attribute that's stored in this relation, you have to specify or list, the data type. Here I'm gonna say ID, what's the data type? Whatever, I'm gonna use a string, for example. Of course, we're gonna use a char or varchar, but we're gonna cover this one later. For example, name, you say string, and department name, string, and the salary. Let's say I'm gonna use double. Of course, we're gonna use different data types, but assume this is the schema. For simplicity, we can just list the list of attributes without, mention the data type for each attribute. That's the schema for this relation. Okay, the schema for the whole database, it depends how many relations do we have. I'm gonna just have the collection of just listing the schema for every single relations that belongs to this database. Okay, good. So here, just to try to find this mathematical notation, how can we formulate whatever we talk about? Assume that we have a list of attributes A1 to AN, and this is the name of the relation. Generally speaking, we're going to notice that during this class, if I use the uppercase letter, I just denote the schema. If they use the lowercase letter, this is the instance of this relation. Okay? Just for simplicity. It's going to be clear from the context when you say the schema, or what do you mean? Whether I'm meaning the schema or let's say the instance of the relation. Anyway, this is the schema for the simple case. We have the list of attributes. I just eliminate the data types, okay, for each attribute. Then the relation R, in order to try to find a way in order to formulate that, I'm gonna relation R, which the relation instance over the collection of the set, the domain values, can be defined as following. In other words, we can use the Cartesian product in order to build or create what's called the population, or they say all the possible value that we can get. Let me go back. I think I'm going to use this one here. So assume that we have, for simplicity, you have a relation R that has attribute A and B. And attribute A is gonna have, for example, let's say A1, or let's say AB, let's say Alice, Bob, let's say, and this is computer science and math. Okay? So this is all the possible value for each attribute. So relation A, the set or the list of all possible names that's stored in this relation, it might be Alice or Bob. In the list of all the possible value that for the department can be computer science and math. Okay? Then now I need to find an instance. What does that mean, an instance? The instance can be represented as a Cartesian product. And I'm going to use the Cartesian product just to try to find a way in order to combine the data that belongs to the different domains. For the A, the domain A is going to have only Alice and Bob. And for the domain B, it's going to have only two valid entry, computer science and math. Just an example in order to find a way how can you represent that. Then, if we got the relation R that contains this attribute A and B, it's going to have Alice and computer science. We call this one valid instance. Why? You study, the statistic, and you know that what you mean. The population, that means is the entire group that you want to draw the conclusion, for example, about, which in this case, all the possible, let's say, instance value that we can get, a sample is going to be like specific group, or like that you want to collect data and etc. So anyway, here the relation R, this one an instance. How can you tell this is valid instance or not? Because here, if you try to find, let's say, the whole instance, the complete value that we can produce here from this relation, based the value of A and B, and they have all the possible, let's say, domain that we have, we can build Alice. It's gonna be with, let's say, computer science, and Alice with math. This is the possibility that we have. Alice is gonna be either computer science, or maybe Alice is gonna be either with the math. And here we have a Bob. It's gonna be with computer science and math. This is, the population, or the entire set, or the entire group for the instance that we can get. Any instance you have in the data must be subset from this group. So in this case, you cannot have Alice, for example, or have Alice, for example, computer science and, let's say, physics. Because if you compare this one here, we never have this entry or instance of this data is going to be in the population, because based on the, what is called, the list of all valid domain that we have, this is, the entire instance that we can get. And any instance, in order to be valid, and to be legal, must be belongs or subset for the entire domain that we have, or instance that we can get. Clear? So that's what we have. So for example, give you example, assume that the domain of the student ID, this value, and the student name, those are domain, and the measure is going to be 3 measures. So if we have one instance, for example, for 1-2 Smith, and let's say computer science 307 Jones, etc., you see all of them is going to be valid entry or valid instance. Why? Because if you compute the Cartesian product between the student ID, student name, and measure, and just you need to do what? And try to perform Cartesian product based on the list of domains that we have, with the list of all possible attributes or values that in each domain. Definitely you can specify, you can tell whether this instance is going to be part of the valid instance or not. Anyway, this is the way that we perform. We have relations, and every single instance it can be constructed based on the list of the attributes or the domain that we have. Most important part here, the relation must have 2 parts, schema and instance. We'll see more details, this organize the structure of the data that we have, okay, which capture or describe the structure of the data. And the second one here is going to be like the instance is going to be the table, which is going to be just specify the status or capture the current state of the data. Okay. One more thing about this part here, you can say for every single instance of the data must be the subset of the population that you just built based on the Cartesian product. So if you have, for example, if you have any instance of the data that contains information is not exist in what is called the population data that you just generate based on perform the Cartesian product of all the possible domains that we have, then the instance is not valid. You never have this one. You cannot have this one. It's never exist. Okay, now we generalize our definition. We talk about the schema of one relation and the instance of one relation. We know that the database is going to be composed of the collection of what? Of a set of relations. Okay? So the logical, when we talk about the database schema, that means for every single relation that we have, you need to define its schema. Then after that, you're combining all the schema together, you're going to say this is the database schema. For example, in the relation university, we have an instructor, maybe you have a student. And the student is going to have a specific schema here. So when you talk about the database schema, I'm going to say the database schemas are composed in two schemas. Each is going to represent one relation that belongs to the database. And the assumption that we have only two schemas that belongs to this database. The instance of the database, or database instance in this case, the snapshot, or we say for all the data in the database in general. So in this case, since we assume that we have only two relations belongs to this database, so I need to take a look at this instance of the instructor and the instance of the student, put it together, and I say this is the instance of the database that we have. Clear? Just generalize what you have here. Good. Now this is what is called the first part that we talk about when we said we need to have, the relation model is going to define three concepts, the structure. Now let's take a look at the second part, okay? Which in this case, the integrity or the integrity constraint here. So integrity constraint, that means, generally speaking, is like a condition or set of rules that must be imposed or must be enforced or must be true for every single instance of the data. So if you specify that, a rule stating that the GPA must be between 0.00 and 4.00. So that means you will never find any tuples has a GPA beyond these values. So in this case, assume that you have a GPA, you will never find, for example, GPA 5.00. No way. Because I enforce somehow a set of integrity constraints. I specify the GPA must be between 0.0 and 4.00. Okay? So it looks like you have a set of conditions, set of rules, you wanted to enforce them. Yeah? Good? How can you do that? I can't tell this one at the beginning of the system. It looks like when you write your code, you have if statement somehow, or validate the entry. But of course, we are not gonna hard code this one. When you build our data or create, say, a table, you can specify a set of rules for each entry. You can specify for the GPA must be between 0.0 and 4.00. Let's say for the department name, you can specify this one, the valid entry, computer science and math. That means for every time we try to modify, try to insert a new tuple, the database management system is going to check all the set of constraints that we have, or to say the rules that you set. And they're going to tell, I'm not going to allow any modification of the data that violate any of these rules. So if you specify the set of rules, you're going to have or end up that all the database instance or the instance of every relation, we call that legal instance. So this means all the relation, or we say, in this instance of this relation must satisfy all the specified integrity constraint, all the set of rules that you specify on the database, on your data. Okay? Good. That's what we did in this part. So that's what's called integrity constraint. How can you do that? So we need to find a way in order to enforce these conditional set of rules in the relation. In other words, we need to find a way in order to impose these conditional rules. One thing we can perform that, when you create your table, you have to specify this set of rules. But we need to find a way in order to do that, okay? The first thing, or the first rule that I'm gonna perform, or take a look, is called the key, okay? So I'm going to introduce to the key notion, which is a very important notion that we take a look here. How can, for example, specify or identify, for example, unique tuple in the table? How could you tell? How can I specify a specific student in this class? It looks like I need to use unique, let's say, attribute or set of attributes using them can uniquely identify any student in this class. For example, let's say you can use student ID. So if based on the student ID, I can uniquely identify a specific student in the class. So it looks like you have a set of, let's say, attributes, maybe one or more. Use them, you can specify, you can identify any tuple in the relation. Okay? So the key is one form, the integrity constraint, which allow me in order to identify a unique tuple of the relation. Allow me in order to perform the search in the relation. Okay? One of them, if you are familiar with the terminology called the primary key, foreign key, that's what I'm introducing you here. For example, how can you tell or specify that the student ID must be unique in the table? There's one constraint, one condition. Yeah? How can I enforce that? I cannot say, for example, I need to do it. Without the database, the simple thing you're going to perform every time you add or try to insert a new student ID, I need to search the entire data to check whether this ID already exists or not. If it already exists, I'm going to reject your insertion or your query, or the command you said. I can't because I already have the student ID. Yeah? Of course, we are not going to do this one. We have a smart way to perform that in the database using what is called the primary key. So how can you define this one? So again, the key is very important. It's going to identify, for example, allow me uniquely identify any tuple of the relations, which is going to be part of the, let's say, integrity constraint. I'm going to start defining what is called the super key. Then after that, I'm going to extract the candidate key. Then after that, I'm going to define the primary key. Okay? So assume that you have a schema R, okay? And inside the R, this means you have a set of attributes, whatever. Okay? Assume that we have a subset of attribute with K with subset of the relation R. For example, if relation R is going to have A, B, C, D, maybe K is going to be A or AB or ABC or ABCD. Okay? Or any combination of them. Okay? So K can be or defined as a super key if using this set of attributes, we can specify that there is no tuples in this relation. It's gonna have the same value for those set of attributes. Let me increase this one. Assume that we have student ID, name, GPA. 1, 2, 3. Okay, and Alice, Bob, and maybe you have Alice. 1, 2, 3. Okay, so in this case, assume that I've said the super key is going to be the ID and name. And now I need to test this one. So based on the definition they said, if you specify, said your super key ID and name, this means you will not find two tuples, okay, in this relation. Of course, two or more, okay? Two tuples in this relation going to have the same value for this set of attributes, for the ID and name. So let's take a look at my relation to check whether it's going to be a super key or not. Now I'm just focusing this set of attributes. Did you find any two tuples? They're going to have the same value for the ID and name? No. This one is going to have 1 and A. This one has a 2 and B. They are different. This one is going to have a 3 and A, but they are different because the ID and name, they have two different values. So in this case, I can say the ID and name are the super key. Clear? Another thing. How about, let's say I'm going to say K1 and K2. Another key with a subset of relation R. Assume that we're going to say ID. Whether the ID itself is a super key or not. Let's apply the same kind of, description or definition of the super key. This means you will not find two tuples or two different tuples. Of course, must be different, not the same tuple. Okay? Can have the same value for this set of attributes for the ID. So let's check my data here. Do you find any two tuples? I'm going to use a different color here. This one, the orange. Do you find the two tuples, they have the same value for the ID? No, it's ID 1, 2, 3. So in this case, this is super key. How about another example? How about what if I said K3 is equal name? Is the name is super key or not? Let's check. What do you think? The name is super key or not? No. Why? Because I found two tuples, they have what? here A, and they have A. Both of them are two different tuples, but they agree in this value, so in this case is not. For the GPA, based on this instance, it might be, yeah, because we have three different values. But we don't use this one because we expect that the GPA maybe have multiple students, they're gonna have the same GPA. But based on, yeah, can repeat of course, and etc. But based on this instance, you can tell. Maybe you're gonna say, yeah, based on this instance, yes. But here we specify our condition in this relation. So that's why we need more data in order to tell, in order to describe or have more, in order to define more accurately, I mean, the primary key or the super key in general. So this is the super key. So the candidate key is like any super key must be super key, so must satisfy this condition plus something more. We can, and we said any super key is a candidate key if k is minimal. What does that mean is minimal? That means you cannot break it down into, let's say, a super keys or subset of the super keys. For example, we said the ID and name of super key. Yeah. Let me do this one again here. We said the ID and name are super key. Is the ID and name is a candidate key or not? No. Why? Because I can't break it down to, let's say, a subset of attributes. At least one of them is going to define or going to be like a super key. So here in this case, I can say this ID, and another key is going to be the name. Right? So you see that the ID is super key by itself. So in this case, I can say the ID name together, the set of attributes ID and name together is going to form what's called the super key, but they are not candidate key because I can't break it down to the subset of attributes. At least one of them is going to satisfy the condition that can form super key. So now we know what do you mean the super key. We can distinguish what do you mean the candidate key. The candidate key must be super key, but it's minimal. That means you cannot break it down to the, let's say, set or subset of super keys or subset attribute that at least one of them is going to, let's say, provide or let's say from the super key. How about the ID and the social security number? Is it super key or not? Based on your information, based on your knowledge, is ID and combination of ID and social security number, both of them are super key. Perfect. Are they candidate key or not? No. Why? Because if you break it down, you're going to have the ID and you have a social security number. And both of them individually going to form super key. So in this case, this one is going to be super key, but it's not going to be candidate key. So the ID by itself is going to be super key and the candidate key. Social security number is going to be super key and at the same time can be candidate key. So we need to add one thing to the candidate key. We're going to say the candidate key can have null value. So the social security number is the super key and the candidate key, and we can add more property to the candidate key, states that the candidate key can have null value. So when you say the social security number by itself is the super key and the candidate key, okay, might have a null value, okay? What's the primary key? The primary key that you can choose whatever candidate key that we have, but make sure this candidate key cannot have null value. So in this case, we are going to use a student ID. That's why if you take a look to your, the information that's stored in the IIT database, we are going to rely on the student ID in order to uniquely identify any student in those universities. Why we cannot use the social security number? Social security number is candidate key, but we cannot assume that for every single student must have a valid candidate key. When I came here as a foreign student, I don't have a social security number, so they cannot find information. They cannot uniquely identify me. That's why they use like the student ID. So again, it might be the candidate key might be going to be super key, yeah, which cannot be break it down, and it might have a null value. It might be. So I'm trying to avoid the one that has a null value and choose one of these candidate key as a primary key. Back to this question that you got here. How about the student ID? This is student ID name, and the other one what? Let's say ID. Let me write this one. Use different here. Just click over this one again. Don't tell me I need to click this one again. Yeah, here. So the ID and the name or the social security number and name. Assume this relation R. It contains all these attributes. So how about the K is equal ID, social security number, and name? Is it super key or not? Yes. All the list of a set of attributes that for the relation is gonna be super key. Okay. So okay, is the candidate they say candidate key? No, because I have the ID, one key. I have a social security number. It's gonna be each of them is gonna forms what's it called? I mean the super key, and also you have ID and name together, and you have the ID. Let's say social security number and name together. There's another forms of the super key. So in this case, it's not gonna, I mean, forms a candidate key. Okay, so the primary key, as I mentioned, you have a set of candidate keys. You have to choose one based on the domain that you're going to use, and make sure that this candidate key that we use as a primary key must be not have null value as a possible value. Okay, this is one of the main distinguish between the candidate key and the primary key. Okay, primary key cannot have I mean the null value. The primary key must have value. When you use the student ID, this means I cannot store information about the student. I'm gonna say, oh, this one doesn't have student ID, so I'm gonna keep this one blank or not. No, it's not allowed. So when you create your data, now one way in order to enforce that the primary key or uniquely identify any tuple of the relations, if you specify this ID, it's gonna be, for example, char 10. You can say this one, this is a primary key. So this one way to enforce this integrity constraint. So the system knows that this value you cannot have two tuples that are going to have the same value based on the ID, because this is the primary key. This must be unique value or unique item, unique attribute within the whole instance of the data. Okay? How to enforce this one? They're gonna have different ways. The simple thing they're gonna perform, they're gonna build later. We're gonna work with the index, talk about the index. You're gonna build an index. Then the index is gonna have unique IDs value. Then here you're gonna have a pointer, where each tuple is gonna contain this information about this ID. So when you try to insert a new value, the system is gonna check the index. If you found this entry here, you're gonna reject this one. You're gonna say, oh, you're gonna violate the primary key constraint because we already have a tuple that has this value for the ID before. Then you have to react. So generally speaking, relations primary key uniquely identifies single tuple. We agree with that. And sometimes some database systems are used here. If you didn't specify, for example, or define one primary key in your data, they're gonna do this one automatically. Later we're gonna see when you create tables in our database, we can specify which one is going to be primary key, etc. If we didn't specify this one, the data is going to be we're going to automatically build one, because we need to find a way in order to uniquely identify the table or the data, tuple within the relations. Okay. There is many database management systems support the auto-generated keys. We're going to try to cover this one later when we talk about the SQL. So in this case, I don't need to have that manually generated the ID. Specify for every single student specific ID in order to uniquely identify this tuple in this relation. So maybe you can use sequence, maybe use auto-increment serial. So it looks like we have internally it's gonna have add one tuple, or maybe add this tuple, for example, let's say call this one ID, and you define this one, for example, as serial. So in this case, when you try to insert the data, you are not going to insert this ID. The system is gonna start, for example, 1. Every time you search in your tuple, it's going to be 2, 3, it's auto increment this one. So we're going to use this one in order to modify the data, in order to access the data, in order to uniquely data. Personally, I prefer using I mean the manual one, because you have a specific ID here. Because here you need to take care, for example, every time you modify the data, delete this entry, maybe we are not going to have these IDs going to be auto-increment. Maybe we're going to have some gaps in the middle. And this one maybe has full control about your data pattern. We're going to cover this one later when you talk about the indexing technique. Right now, keep in your mind, there's some database going to, if you didn't specify a primary key for one attribute in this relation, you're going to automatically build one internal, okay? Now back to your question. How can you relate relations to relational attributes that belongs to relations, which what's called the foreign key constraint here. So sometimes you have, let's say, student relation, and you have ID, etc. I'm just interested in the department name. Okay, then we have another relation we call department, which contains all the information about the department. For example, the location, a building, more detail, who's the head of this department, and the budget of this department, many information. Okay, so here, assume in our database we have, or university, we have computer science and math. So only have two tuples here in the department, yes? Because those are the department in our university. Okay? So here I need to make sure that what? An entry, the department name value here, the stored here, must exist in other relation. So I need to enforce this constraint because I need to make sure my data is valid. Remember we talk about the domain or Cartesian product, where we try to build the population or all the list or any instance. A valid instance must be a subset of the overall instance that we can create based on the domains of the old value that we have. So in this case, I need to make sure that if someone try to insert new tuples here, and this one gonna say for the department, maybe gonna say physics, the system must reject this one automatically. In other words, if you try to insert a new student that belongs to a specific department, the department must be exist in the department relations. Otherwise, this is not valid entry. You get this one? If you try to extract information or register a student for a specific course, let's say you have a course. Let's say the course ID and etc. Let's say CS 425, CS 525. This is the only courses that we have in the IT. Okay? When you student try to register for this course, let's say takes. We have a student ID. Okay, the course ID, of course, semester and etc. many information. I need to make sure that for the takes relation, when you have keep tracking for the list of all the student ID must exist, must be valid student, must be registered in the university. How can you get this information? I will connect this attribute ID with the student relation. So every time you try to insert a new student that takes or keep tracking, you say what course is taken by this student. When you list student ID 1, for example, the system automatically gonna check, we see whether this student already registered or not. So whether this student already here or not. If not, the system gonna reject this one. Another thing, when you try to insert, let's say new tuple, student 1 takes, let's say, course CS 458, for example. You try set 458. The system automatically must check this one to see whether this course ID is already exist or valid entry, or let's say a course offered by the IT or not. So it's gonna try to check with the list of the course here to see whether the courses exist or not. That's what's called the foreign key constraint in general. So you can specify that an attribute, maybe one or more attributes, okay, from one relations has to map to another tuple in another relation. Must be exist there. Clear, guys? So the set of attributes inside one relation, we call this one referencing relation. So let's write this one here. Okay, I have another example in the next slide. Okay, it's gonna be more clear here. So the set of attributes inside some relation, we call this one referencing relation, which in this case, the takes, we call this one referencing relations, and the set, or they say the primary key of another relation, we call this one referenced relations. In this case, it's gonna be reference relations. Okay, I will get back to what we call the referential integrity then after I go to the example. Okay, let's have example here. Assume we have what? Student relation, which contains information about the student. You see student ID, social security number, name, address, phone number, GPA. Do you have any problem with this relation? No, it's going to capture information about the student. What's the super key, or let's say what's the candidate key here? Either it's going to be ID or the social security number. And we use the ID because the social security number, we cannot guarantee that every single student have this value, can have this value, or valid social security number. Unless you said in your university all the students must be citizen or must have social security number, then in this case you can use this one as a candidate key, or as a primary key. Okay, so this is the primary key. Do we have any problem with this part? Let's do step by step. Let's see. No. Good. The second relation called course, which contains information about all the courses offered in this university. Assume we have those courses, only 2 courses, okay? CS 457, CS 255, and etc. Okay? So this is the course ID and the course number. Okay? So you see, we have both of them going to be candidate key. I can use either of them as primary key because the course number never can be null value and the course ID never can be null value. Acts like redundancy, we can use the course number here as the primary key, but assume that we're going to, for simplicity, I'm going to use the course ID as the primary key. Do you have a problem here? No. So far, so good. Now, I need to build the report. So far, I didn't talk about the, let's say, what's called the foreign key constraint. Now, in order to build the report, so this report, you have to list all the courses taken by every single student in which semester with the grade. That's the report. It's going to contain this information. Okay? When you try to perform this operation, sometimes you're going to insert some data here. So I need to make sure that this report or this relation cannot have or include invalid entries. Okay? So how can you enforce this one? You see that I'm going to have the student ID, the course ID, and the semester, and the grade taken, or whatever, the grade of this course that's taken by the student at this semester. Okay? So I need to do what here? In order to make sure that we have all the valid, the entry for the ID, or the student ID must be student reside or stored in the student relation. All the courses here must be valid course offered by university. That means the course ID here must be here what? Somehow stored here or already there in this relation in order to have a valid course ID. Okay? How can you enforce this one? I'm gonna say, let me go over this one again. This first, what's the primary key here in this relation? It's gonna be the ID, student ID, the course ID, and the semester. Must be all of them. Okay, this is the primary key. I can't say the ID, student ID, the course ID only the primary key because the student maybe retake this course over and over, many times. You can't repeat this course. That's why I need to specify the semester. Okay, good. The other thing we can think about here, how can you enforce this when you have all the values going to be valid? So in this case, I'm going to say this ID, okay, in the grade report must be somehow connected with the ID of the student relation. So in other words, if you have any ID stored here, this one must be valid entry, must be this entry exists in the student relation. That's what we call foreign key constraint. I'm going to say the grade report is going to be referencing relations, and the student ID here in this relation, or this attribute, it's going to be foreign key for the student ID that's stored in the student relation. And the ID that in the reference relation must be the primary key. That's what's called the foreign key. So here you will never find student ID that does not exist in this relation, in this grade report, based on the constraint that we have. For the course itself, you will never find the course that is not listed here in the course in the grade report. So we have another thing, another constraint. We're going to say this course ID is going to be foreign key constraint with this course ID. It's like a connection. So by doing so, every time, try and manipulate, try to insert the data, try to modify, for example, assume I'm going to change the course ID of this one says 525. If you do this one, the system gonna check, you say CS5 to 5, this one form constraint. I need to check the course ID in this course to see whether this course they try to insert or the value is already listed here or not. If yes, I'm going to allow you to proceed. If not, I'm gonna reject this. I'm gonna say, no, you cannot, you have violate what's called the foreign key constraint. Clear? We have another thing, like what is called, another terminology. We call this one referential integrity. So the foreign, this is, the general, let's say, notation. We call referential integrity. That means specify that an attribute from one relation has to map to the, let's say, a tuple or another attribute, another relation. Okay, and here for the referential integrity, we don't enforce that the attribute in the reference relation must be primary key. Most of the database management systems don't do that. Most of them implement the foreign key constraint. That means in this case, you have relation R, S, you have A, B, and A, C, D. I'm gonna connect, say this is a reference relation and this reference relation. This one must be primary key. So we try to have this A from the relation R. It's gonna be reference or the attribute A in the relation S. This one must be primary key. For the referential integrity, they relax this constraint. They said it might be not the primary key, any attribute. There is no need to be primary key. But as I mentioned, most of the database or all of them, they don't implement this one. They implement that the foreign key constraint must be the attribute that reference and the reference relation must be primary key, nothing else. So here, we try the ID here, the foreign key. The ID here must be the foreign key, and this cross ID must be the primary key of this relation in order to satisfy this condition. Otherwise, we cannot do this. Okay? This is just, how can we depict, the schema that we came up with. We're going to take a look later when we talk about the entity relational model, that when you start to design your database, you have different ways in order to find a way in order to represent the data. It's going to be easier for anyone to take a look at this structure and say, okay, it looks like you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 relations. And here the content, the name of these relations, and this is, they say the content, we'll say the list of attributes of this each relations. Generally speaking, we're going to use, for example, how can we tell whether the attribute is a primary key or not? And it's going to be underlined, okay? For this case, the ID is the primary key of this relation. Here for the department, going to be the department name, for this relation. This one arrow from the reference relation here, this might be easier. You see that this is the course ID, is the primary key of this course relation, but it's going to be what? It's going to be like a foreign key, because this one must be connected with a primary key department name here. So generally speaking, we try to draw that. I'm going to use an arrow, directed arrow that has one arrow from the referencing relation to the reference relation. Okay? We're going to cover this one later in more details when we talk about the entity relation model. Okay, now let's take a look at the part that is supposed to start talk about today. The data manipulation. Now the third concept. How can Access manipulate the data? So we're going to talk about what's called the data manipulation language. In more details, we're going to talk about, the relational algebra. Okay, so take a look at the language. Allow me to store, retrieve information from the database. Okay, before we specify the data manipulation language into two parts, the first one procedure, the second one non-procedure. You see some text box, they have different, classification, but this is, the most common one. So what does it mean for the procedure? So when you choose procedure, you are going to tell me exactly what information you need and also tell me the steps, how can we get this information. That's called the procedure. Non-procedure or declarative language, you are going to just to tell me what information you're looking for, but you're not going to tell me how can I get there. So we leave this one to the database management system. It looks like you say, take your time, figure out whatever the best way in order to find or give me this result. The procedure one, the one that specify in a high level, of course, what you need to find and also how you get this result. We're going to take a look to the relational algebra. I think you are familiar with this one. If you database, or sorry, data structure class. I guess we covered this one somehow. Anyway, the relational algebra, it's like a set of operations. We are going to go over a set of operations that allow me to what? To retrieve, to get data, to manipulate tuples. That means to insert, delete, update, okay, in a relation. It's based on the set algebra. That means we don't have a duplicate data. Later, we're going to relax this one when we talk about the SQL, or the say database in general. We do have a duplication of the data, yeah? Sometimes, as I said, I want to retrieve the list of all, let's say, department in this university. So maybe, or let's say the list of the height, or the list of GPA in this class, or grades of this class. You see that we maybe gonna have A's, B's, D's, and etc. So maybe you have a duplicate of the data somehow. In the relational algebra, it's gonna say, no, you are not allowed to have a duplicate because this relational algebra based on the set algebra. There is no duplicate when you talk about the set. Later, we're gonna relax this one when we work with the database. We're gonna say database might have a duplicate of the data. Yeah. Of course, you have a primary key, but if you remove the primary key, for example, you get student name, department, or they say department and the GPA, maybe you have a set of students that belong to the same department, they have the same GPA. So might be duplicate data somehow. Anyway, in order to write this query, it looks like we're gonna give me a set of operators. I'm gonna use them, and each of them, or these operators, assume that they're gonna have at least one relation as input. For example, we didn't talk about this one. Let's say Cartesian product. You have relation R and S. I'm gonna perform Cartesian product or join them. Then I'm gonna produce the result, project a set of attributes. So maybe have one or more attributes, let's say relation as input, perform one operation, then produce a result. And the result is gonna have another relation. Okay? You can take this result and feed into another operator in order to perform another operation, etc. That's what you call a chain, the operators, to get more complex operation. For example, I want to list all the students they take this course, okay, in this fall. You see, they have many constructions. Many constraints, many complex operations you need to perform. I need to find the list of all the students, okay, they take specific course at a specific, let's say, time frame, okay, and they are from a specific department. So you see, I cannot do this one in one query, so I have to have many steps. First, extract the list of all the students, okay. Then after that, filter out only, or keep only the one that belongs to specific department. They talk specific course. Then after that, you can add more constraint in complex query. Okay. Again, the relation is a set of tables. Relation cannot contain duplicate tuples. Okay. And when you talk about the relational algebra here, you're gonna see that we need to require that duplicate must be eliminated. But later, or actually in real data, when you try to work with the database, tuples might have a duplicate in the value. It's gonna be more clear later when you talk about this one in more details. Give me 1 minute, okay, just to show you what kind of operation, then we're gonna go over this one next lecture. So we do have six basic operators: select, project, union, set, difference, product, rename. Then we are going to add more later. This is the six basic operations that we use in the. Right now, we're going to take a look to the basic operators or operations we can use here: the selection, the projection, the union, the set, difference, and the product and rename. Then after that, we see that maybe we can enhance, maybe we can show you that different, or let's say advanced operators, you can use them. Then after that, I'm gonna show you the extension of the relational algebra. So in this case, I'm gonna give you more, operators which make our life easier, okay? So the first one, we're gonna take a look at the selection. Sometimes you wanna do what? You wanna retrieve the data from relation. Either it's going to be one or more relations, okay? Most of the operators allow do what? To X two or more relations, one or at least one relation, perform some operation, then it's going to produce another relation. You can't take the result and plug it or fit into another operator in order to perform another relations. For example, you can access the relation, then after that you can filter out or only select the tuples that satisfy specific condition. Then after that, you can specify what the list of attributes that you want as a result. You see that? It looks like you have like a chain of operation. So the first one, selection. We're going to use the sigma here. When there's a selection, that means you're going to select a subset of tuples from a relation. So it looks like you have only, you don't want to, the entire tuples that's stored in this relation, only the one that satisfies specific condition. Okay? Let's go over this one at a time. So the first one, selection. So if I ask you the question, for example, select the number, let's say, the list of all the students there in, for example, the CS425 class. So it looks like you need to what? You have to go to the specific table. Then, of course, based on the schema, if you don't have access to the schema, so you cannot answer the query, by the way. You know that, huh? Yeah? So that's what applies. So have a schema. Assume that we know what's going on with the schema. Actually, we're going to use the university schema. Okay? So in order to access tuple one relation, and you need only to filter out or only produce the tuples that satisfy specific condition. What condition you're going to use? It depends on the question, the query that you perform. Okay? We're going to use the way that we write that. I'm going to use the selection. This is how can you write, for example, I want to select all the tuples from the relation R that satisfy specific condition. The condition, we use the predicate P here. And this is the relation R. So that means I'm going to access the relation R. Then after that, I will only filter out the list of the tuple that satisfy this condition. Now we're going to take a look to the condition, how it looks like on the side here. How can you formulate my question or the condition that I want to enforce, make sure that whether the tuple is going to satisfy this one, going to be survive, otherwise it's not going to survive. Another way to write the relational algebra, we can use expression tree, which is the one that I like. I will use both of them. So here you're going to have the relation R first. So start with the bottom up. You are going to access the relation R. Then after that, for every single tuple from the relation R, I'm going to enforce that I need to perform this condition. So it looks like for I equal from 1 to the last tuple in the relation R, if the condition is true, then display this tuple and continue this operation. Okay? Clear? You hear me, by the way, yeah? So far, so good.
Yes.
Good. So now let's have example here. If I ask you, here the query that you try to answer, I've said here, select those tuples of the instructor relations where the instructor is in specific department. So in this case, how can you answer this query? You have to take a look to the schema. And based on the schema, it's going to tell, for example, where I can get the information that you're looking for. Whether do I need to access 1 or 2 or more 3 tables in order to answer this query. In this case, since we have one table or one relation that contains all the information about the instructor, and here said select instructor, okay, the list of instructor in specific department. So you see in the specific department, this is your condition. So the way that you access this one, you need to iterate over every single possible tuple of this relation. And here you need to just to check whether the department name is equal physics. Why I choose this field in order to put this one in my condition? Because I know that they asked me, they said the department name is equal physics. So this is the way how to can write my query. You have to insert or access to say the instructor. Then after you access every single tuple, I need to check this condition, which here the department name is equal physics. Then he is gonna produce the result. So the system gonna do what? Line one at a time. Start from the beginning. Is the department name equal physics? No. Jump to the next. Is the department physics? No, 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 yes. So what I need to do here, now you have to display. This one is going to be part of the result. You see, Einstein is going to be the first one. Then here, the next history. This is physics? Yes. Now display the whole tuple. And remember, we just want to select the tuple that satisfies the condition. Did they say anything that I want to limit the result to have like specific number of attributes? No. So the result here, the selection, is not going to change the degree or the artery of the relation, but it's going to change only the number of tuples that we can, let's say, produced as a result. It depends, of course, on the data. So I can't tell, for example, how many tuples are going to be produced because it depends on the instance of the data. Here, based on the instance that we have, the result going to be the query going to be evaluated, and this is going to be produced 2 tuples. Maybe if you have a different instance, the result might be different. Okay? What if I ask you select the department equal, let's say, XYZ, and the department never exists? So as a result, when the system tries to check XYZ, I'm not find any department in this name, so the result is going to be something like this. Okay? Only it's going to produce the ID name, department name, salary, and we do have empty relation that doesn't contain any attributes. Okay? So clear the simple one. That's the selection. Can I use, for example, a simple condition here or not? Only, or maybe I can use complex condition. That means you can say, I want to list let's say the list of all the instructor. They are in the physics department, and also their salary, for example, has a specific value, or their first name start with a specific character. So you see that you can build your condition. You can come up with a, you say, complicated. I'm not gonna say complicated, but compounded, composite condition here. Okay, you can compare. We're gonna see that attribute with the constant, or maybe attribute with another attribute. So you have a full control. Let's do this one step by step. So the first one hopefully is clear. Now let's see how can we, for example, what kind of operation we can use or comparison here. The previous one example I said the department name is equal to specific value. So can you use not equal, greater than, less than, greater than or equal, and etc. Yes, we can use them. It depends on you what kind. So you can decide what kind of or the right comparison, sign that you're going to use based on the query that you have. Okay. So the symbol, or they have a selection or condition, either you're going to have an attribute, which in this case, for example, department name, salary, ID, or whatever, and you can use operator here. You can use, for example, greater than, or you say a comparison here, greater than, less than, not equal, etc., with the constant, or maybe attribute with another attribute. You can say, for example, the ID is, or let's say the department name is equal the building name, for example. We assume that we need to list all the instructor, their department name has the same name as the building name, something like that. So you can compare, two attributes together or against each other. So can I make, for example, combine several predicates? Yes. I can use and, I can use or, I can use not. You can say, for example, you have one condition. When I say condition here in this case, so the condition might be attribute, or let's say operator with a constant or with another attribute. Then you can say and with the condition, the same structure, or the same, let's say, form, and you can add, for example, let's say one condition, let's say, and another condition, and you can say or another condition, and you can use the parentheses in order to specify the order of this one. We're gonna have some examples about this one later. Okay, so you can build whatever predicate that you want. Of course, you try to find. You need to come up with the right one. Okay, it depends on the query. Let's have another example here. Find all the instructor with the salary greater than 90,000. So I need just. So you see, based on the schema, you can tell which relation it looks like instructor. I need to find the salary greater than 90. I'm lucky because the instructor relation is going to contain the, let's say, field called salary. So I know which field I need to use. I know which relation. So it looks like I still need to access only one relation in order to answer my query. So in this case, remember, select all the instructors. So it looks like you need to filter out the tuple that only satisfy this condition. It's going to be part of the result. So selection, yeah. Sigma, you say the salary. Let me write this one here. That's so an instructor. Access. So for every single tuple, I need to make sure the salary is greater than 90,000. So here it's going to be evaluated one at a time. And this one, the only one, it's going to be X, or it's going to be the list of the tuple. It's going to be part of the result. Let's say this one, and let's say this one. So we have only two tuples, yeah, in this case, based on the instance of the data. That's why we said we're going to use the schema in order to formulate our query. Then we are this query is going to be evaluated based on the instance of the data that we have. So if we give you, for example, instance of the data that contains the following information, and I ask you, give me the result after you execute this query. So based on this instance that we have, you can tell me, for example, what the result is going to be here. So here going to be ID, name, department name, and salary. And here it's going to be, give me, say, 2222, the rest. And the other one is going to be 83821, and the rest of the information for the name and department and salary. Okay? Have another example here. So how can we have a combine maybe 2 or 3 conditions together? Give you a relation R. This is the information that you have. This is the instance. And this is the schema. You can say A, B, C, D. This is the list of attributes that we have. And I ask you this question, for example. Select A equal B and D equal 5. So here it's clear that we need to have 2 things here. Yeah. The first one, let me make sure here. So I need to make sure this tuple is going to be part of the result F. This tuple must satisfy this condition. So A must equal B. Those must be equal. And D must be greater than 5. So for every single tuple, one tuple at a time, you need to check whether A equal B, yes. Whether D greater than 5, yes. So this one part of the result. This is the first one. Then the second one, is A equal B? No. Since it's AND, you know AND must be evaluated. You have 2 conditions or 2 expressions must be evaluated to the true, both of them true. Yeah, in order to the overall result is going to be true on this part. Yeah, or this means either is going to be true is going to be part of the result. Yeah, so in this case, 2 condition must be evaluated to the true in order to select the specific tuple or particular tuple. Here, no, the last one, A equal B, yes, and D is greater than 5, so it's going to have only 2 tuples in this array. Clear? You see that the array we still have 4. In the selection, when you filter out or select number of tuples, you are not going to affect, the number of columns is going to be part of the result. So you still have 4 columns, but the number of tuples might be changed. It depends on the data or the instance. Maybe all the values that satisfy this condition, A equal B, and D is greater than 5, so we are going to produce the same relation. Okay? Please feel free to interrupt me if you didn't catch something or you have a question. The other one here, I need to do what here? There's 2 things that will combine 2 conditions that we did before. Find the list of the instructor in the physics department with the salary greater than 90,000. So I need just to combine both of them. So what do you do here? I have to ask the instructor relation. And I do have the first condition. It's going to be department name is equal physics. That's what I did here. And the second one, salary, I know which attribute based on the formation of the query that I have, greater than 90,000. So, and the salary is greater than 90,000. So I need to make sure that only the department is physics. So this is satisfy the first condition. And this one greater than 90,000? Yes. So this is going to be part of the result. The next one, I do have physics here, but the salary is not greater than 90, so this one is not going to be part of the result. You have only one? Yeah, so it's going to be only this tuple is going to be part of the result that you have. Not this one, only this. Okay? Let's go. Next one. So, maybe I will ask you, for example, to select I will try. Remember, we said your comparison of the condition may be involved that you compare attribute with another attribute, because what we did so far, we just compared, an attribute with a constant. Attribute with a constant. So I need to compare, for example, attribute with attribute, for example. So if I ask you here, I want to find all the departments, or list of all the departments, okay, whose name is the same as their building name. Okay, so it looks like their name of the department, which is the department name, is similar to their building. Yeah, and they give you this relation. Just here the instance, and we change this. The department looks like something like this. Has the department name, building, and the budget. This is the information that we have. Actually, this is the information that we have in the department relations. Okay. So in this case, you need to do what? You need to make sure you access this department relation, because all the information that you need is in one relation. So I'm going to go access the relation department. Then here I'm going to select the tuple that satisfies this condition. The department name with this, attribute, because this whose name here is same as their building name. And I know the building name, that information can be stored in the building attribute here. So I can use department name is equal building. Clear? So the only result here is gonna be here, for example, what we have here. Do you have anyone department name is equal building name here? I didn't see anyone here. So it's gonna be blank. Okay? But remember, by the way, when you write your query, don't say, okay, I'm gonna write this query, but I don't have anything. This query is not going to produce any result. It's fine. You need to find a way to write your query in the way that can work with any instance of the data. So even if you take a look at the instance of the data, because remember, we cannot give you all the possible value. So we're gonna give you sometimes a sample instance of the data, because we cannot give you, for example, 1 million record in the exam, or even when you try to test this one using online or using whatever, you cannot, or say, no, this one is not going to produce anything because I can't find any value of, for example, department name is equal building, so this query is not going to work. No, just write your query, then test your query against the database that we have. So if the select operation returns tuples, okay, it's gonna return tuples most of the case, hopefully. Does it matter what relation is used if the predicate is the same? Generally speaking, when you try to answer a query, remember, you're gonna design your database. So either you have only one relation to get the information that you're looking for, or maybe you need to combine or get the, let's say, the result from more than one relation. So you have to join them, which is gonna cover. So we never give you, for example, here department and give me another name of department, another table that contains the same set of attributes, exact one. This redundancy of the data has never happened. So either you're gonna find the information, or say perform the query based on one relation or more in order to combine. Maybe, for example, I've said the department name is equal building, and the department name, for example, or I want the list of all the instructor where their department name is equal the building. So in this case, I need to get the information from two relations. List of the instructors, yeah? I will do this one later with the Cartesian product. I need to have select all the instructor for the instructor relations, where the department name is from that instructor must equal the department name of this relation, and at the same time, the department name in this department must equal the building for this department. Okay?
Yes.
Good. So we're gonna see that we try to retrieve the information. How can you tell how many relations do we need here? And just summarize, for example, the degree is not going to change. Article of the relation, it's going to be the number of attributes, it's going to be the same. The only difference here for the selection is going to affect the number of tuples, it's going to be part of the result. Okay, now we get the selection. How about that? I don't want to have the list of, let's say, all the information that in this relation. For example, I don't want to have all the information of the instructor. I want only the instructor ID and the instructor name. So we need to specify, for example, only specific number of attributes is gonna be part of the result. Yeah. So for example here, I don't want to have the department name, building, budget gonna be part of the result. I want only the department name. It's gonna be part of the result. So using selection is gonna affect which tuple is gonna be part of the result. But I want to make sure how can you control which attribute is gonna be a part of the result, which is gonna call the project. Okay. So generally speaking, projection has a operation. This means has access only to one relation. You cannot access to more than one relation in order to perform the selection. So for example, you can have a relation, assume that the relation R has attribute A, B, C, and I want only A and C is going to be part of the result. Okay, so how can I perform this one? I can use what is called, projection by, I'm going to say from the relation R, I want only the attribute A and C. So the system, when you perform your query, is going to ignore the attribute field or the field B here. And the result is going to be, I'm not going to affect the number of tuples. The only thing is going to be affected the number of attributes here. So still, for example, if you have 10 tuples, the result is going to be 10 tuples here, but the size is going to be different because I'm going to say only A and C is going to be part of the result. Okay, that's what's called the projection. Make sure that the duplicate rows must be removed from the result. Remember, we talk about the relational algebra. When you define this is the original definition, or the initial definition of relational algebra is a set. That means set there is no duplicate value. Later, when you talk about the database management or database systems or database in general, we're gonna relax this one because it might be we have a duplication. You're gonna see how can we have a duplication. Okay, so let's give you an example here. You have A, B, C here. Okay, and they say project A and C. So when you project A and C, it looks like here, forget this trouble. Remember, I'm not gonna touch the original relation. I'm gonna produce a new relation. Yeah. So here the relation R still has A, B, C, and has the list of attributes, and the specific or the answers there is gonna be intact. I create a new relation. So how it works? I'm gonna go relation R here. Then here I'm gonna project A and C. So it looks like here when you actually have the R bigger, the uppercase. So here we have A and B, which is gonna be this one. So here it's gonna have a new relation here. Now you can feel free to do whatever with this relation. We're gonna see later we can rename this relation, assign specific name to this relation. You can modify the attribute names later, whatever you want. We can do this one later. Okay, that's one thing. So you see that when you said project A and C, we noticed that alpha 1, beta 1, and beta 2. So it looks like we have a duplicate value here. So automatically you have to remove the duplicate value. So we have only alpha 1, beta 1, and beta 2. Okay, how about another thing here? What if I said, let's go to have another example here. What if we said, let me project here C and A for the relation R. What's the result going to be here? What you have said, you can't change the order here. Okay, this is by, I didn't know why you can't see by here. Oh, yeah, okay, you can specify the order. So it looks like get X the relation R, then just put the column C first, then the column A second. So you can't change the order. So result is going to be here C and A. Okay, the result is going to be C here and A, and it's gonna be here 1, 1, 2, alpha, beta, beta. So how about if it said projects, for example, only B from the relation R? So what's the result gonna be here? What's the result here? Project only B. Column B. Exactly. So it's gonna be in this case 10, 20, 30, 40. So you can specify whatever. If you said, for example, CBA, so it's gonna be have the same relation R but a different order. Okay? Good. So let's go on another example here. I said list all the instructors, and then I didn't say all the information. I said the ID, the name, and the salary. So please make sure there's not selection. I just want to ask which attribute is going to be part of the result. It looks like I said I don't like the department name. Eliminate this one from the result. So here you're going to say project, what's the list of attributes, and you can specify the order that as you want here. So this is a new relation. Okay? What's the name of this relation? We don't know. We can modify, we can specify, we're going to see later, we can use an assignment, we can rename this relation and produce or use whatever relation you're going to use. Okay, and any name. So clear here? ID, name, salary, I just remove this one, and this is the result that we have. So maybe someone said, okay, I do have a selection, I do have a projection. I can specify or filter out specific attributes and specific table. Or let's say tuples, yeah? Can I mix them? Yes, we can. How about I said I want only the list of the instructor ID, name, and the salary where their salary is greater than a specific value. And the department name is equal specific value or belongs to specific department. So all information is going to be in the one relation, but you see that we have different operators in order to perform them. So we're going to talk about what is called the composition operations here. So the result here, generally speaking, what? Combine. So the question here, for example, find the names of all the instructors in the physics department. Okay, so here, let me change this one here. What we did here first. By the way, let me write this query like this, then switch to change and see whether it works or not. Actually, you have to go to the instructor. Yes. Then after that, filter out the department name equal physics. Then here, when you filter out here, what's the result going to be here? It's going to be ID, name, department name, salary, and only for the guys that belongs to the physics department. So this one and this one, right? We do have only two tuples going to be part of the result, right? Right, this one here and this one here. Good. Then after that, remember, when you said this operation is going to produce another relation, which can be fed to another operator in order to perform or create another relation. So after I perform a selection here, now I do have like two tuples. I need to say, I need just project the ID, or let's say the name here. Because the question said, I need only the names of the instructor. So here in this case, after I project this one, the result is going to be contains what? It's going to be have name. This is the result at the end, okay? And we do have like two value. Let's say Einstein, and the other one gonna be the gold, yeah. All right. So this is the result that we have. And the nice thing, when you build this one as a tree, you can tell, you can understand what's going on. You're gonna say, oh, it looks like this is data start, X the instructor, filter out only the tuple that I want that satisfy the condition selection. Then after that, I perform the project name. Okay. This is the result. Clear? If you understand this one, how about if I write this query? What do you think? I'm gonna say, I don't have space. Let me try to write this one here, okay? So I said, instructor, I'm lazy guy. Assume this is instructor. Okay? Then after that, I'm gonna say project name. Let's say I have another color. Then after that, I'm gonna say select, let's say, department name. What do you think here? Is this one gonna produce the same result or not? No, why? What happened here? No physics. In other words, no department, no name, let's say, no ID, no salary, yeah? Identify. So I'm gonna, if we do the project first, let's do this. The orders matter here, okay? So let's start with the beginning. You said instructor. Then after that, you said, I'm gonna project the name. What's the result here? It's gonna produce a new relations that contains what? How many tuples here? It's gonna be the same number of tuples. How many attributes is this relation? The new one. Only this. Only this. Only name. Then after that, they said, I want to perform selection where the department name is equal physics. The system gonna say, you produce a new relation, and this relation, I can't find the department name equal whatever, because you have only different attribute called name. You don't have the department name. So in this case, it's not gonna be correct one. So the orders matter, okay? If you perform the selection first, then make sure that you're not gonna eliminate, you're not gonna, let's say, remove the tuple that you need to the higher level. We're gonna talk about this one later, but keep in your mind, the orders matter. That's why when you build or write your query here using the expression tree, so it's easy to imagine and say, okay, access the instructor, then after that, project only one attribute, I have a problem because this one is gonna produce gonna eliminate the list of attributes that I need in the higher level. So if someone said name, it's not working, but it's a different story here. If I said name, maybe you can say department name here. Then after that, you perform projection, but it's gonna be lengthy process here, yeah? So let me write this one, different query. Remember, we don't have only unique query. We have a different way in order to answer this one. So I make it the long way, instructor. Then after that, I'm gonna project the same name and also the department name. Then you perform selection, department name equal whatever physics here, okay? Then after that, I need to project the name. Is this one works or not? Does this one works or not? Yes, no? What do you think? I start with an instructor, project the name and the department name, okay? Select the department name equal physics. Then, after that, project the name. Can I do this one? Yeah, perfectly. It's fine. We can do it. Sometimes maybe this one is gonna produce this number. It's gonna be faster than the one that we used here. It depends on the data. If we have a time later, we talk about the query optimization processing. You see that we do have a different plans we can database management system go over or come up with in order to find the best, the cheapest, the fastest one. So here you start with instructor. Then after that, you filter the name and department. So here, that's what we have. This is the result that we have at this stage, right? Then after that, you said only select the tuple that satisfies specific condition. So in this case here, after that, I'm gonna have only this one, and I'm gonna have this one, all right? So I have the information that I need. Then after that, the project name, I'm gonna say only give me the names here, which is this color, and I'm gonna here just give you the Einstein and the gold. So it works here. Remember that when you mentioned that the difference between the relational algebra and the SQL, etc., we've said the relational algebra is going to tell you exactly use in order to tell the system this is the result that I need, and this is how can I want or ask you to do that. So how can I tell those are the steps that I tell the system. Ask the instructor first. This is the result that I need. This is how I want from you to do it. Give you the steps. 1. Access the instructor. 2. Project the name and department name. 3. Perform the selection. 4. Project the name. Here in this case, those are the steps. Access the instructor. 2. The step 2, perform the selection. Then after that, project the names. So here I give you exactly what I need, what kind of result that I need, and what are the steps that you have to follow in order to tell me or to get this result. In the SQL, we are not going to do this one. Just I want to resolve, then the system is going to come up maybe different plans in order to answer my query. Okay?
I have a question.
Yeah.
Why do we need to project the name and the department, and not just the not just the department, and then filter and then just project the name? Like, why do we do the project name in this part?
I give you like a different ways in order to perform this query. But here, if you, the reason why I project the name and the department, because I need both of them in the higher level, in the later operation. That's why I need to keep tracking them. That's why when I give you the question that when I swap the project the name with the selection here, it's not gonna work. Because if you project only the name, so you're gonna have produce a new relation that contains only name. But I want another attribute which is called department name. So that's why I project them here in this step. Because I need it in a higher level, in the other operation above the tree. Okay? And remember, you do have many ways. You don't need to do this step. Maybe do this one easier. It's fine. Either is fine. But just I want to show you that we don't have a unique solution or simple solution. We might have a different solutions. But if you decide to perform project before the selection, make sure that you are not going to eliminate the attribute that needed in the higher level. Because this is structure, this tree. You start from the bottom and you go up. So every operation you're going to perform, it's going to produce a new relation which is going to use in order to perform the operation. So here in this step, what kind of relation that I need to ask is not the instructor anymore. The relation is going to be produced after I project or perform the name, project the name from the and the department of this relation. Exactly, similar to the compiler battle, yeah. And that's what we're doing. The SQL actual database management system has like a compiler. It's gonna perform the similar operation that the same as the compiler. Not the exact one, but similar. Because when you write your query, how the database management system tell you whether you are writing the right query or not. For example, you're gonna see later when you say select star formulation, if you don't write select, the system is gonna say, there's wrong here. It's like syntax error. Something like this. Then after that, the system is going to use the relational algebra in order to find different plans, different way. By the way, here in the top here, or after you perform this one, both of them, it's going to produce the exact result that I want to do. Or that I want to, I need, or I ask the system to perform or evaluate or produce to me. But the difference here is what? The time. Maybe one of them is going to spend longer time than the other. Yeah? But both of them definitely going to have the same result. Clear?
Yes.
Good. So let's go to the next one here. How about, or sometimes you need to perform, let's say, union operation. So you need to combine, yeah, two relations. You study, discrete, yeah? And you know, for example, you have, let me have, I think I can draw circle easy. Yeah, good. You have one circle. Then let's say a different color, I have another circle. Something like this, maybe big, etc. Then what I need to do here? I need the list of tuples, this one relation R and this relation S. In the union, I need to combine the tuple from the relation R plus the tuple from the relation S. So that's what I need. Something like this. Yeah? All of them. Of course, there is no duplicate. If you have a duplicate value, so I need only to produce or keep, the tuples that belongs, at least appears once. Anyway, so how can you perform union? Union, that means you can perform this one, but you have a conditions. We call this one compatibility. You need to check whether the two relations are compatible or not. So first, if you have two relations, you need to join them. We're going to show you that it depends on the query that you're going to perform. Sometimes you need to perform this operation. In order to get a valid, result, you need to make sure that two conditions are held. The first one, the two relations must have the same attribute, the same number of attributes. For example, if you have a relation R and a relation S, you can say relation R is going to have A, B, this one may be C, D, E. When you try to combine them, it looks like you have, like, let's say, something like this, yeah? And this one is going to contain, let's say, for example, 3 tuples, and each of them is going to have 3 attributes. When you combine them, we have something like this. So, or union, this for the relation R, then I won't try to add the relation S here. Something weird is going to happen here, because it looks like I'm going to end up something like this. Because the number of attributes to relation S is more than the number of attributes to relation R. When you combine them, so it looks like we have a set of tuples has only 2 attributes, and the other tuples is going to have 3 attributes, which does make sense. We cannot perform this one. So I need to perform, in order to perform union, two relations must make sure that the number of attributes in both relations are the same. Not one has 2 attributes, this one has 3 or more. No, we cannot do this one. This is the first condition, clear? The second condition here, you need to make sure that the attribute domains must be compatible. What does that mean here? If you have 2 relations, just an example here, relation R and S. Relation R, for example, has the same number of attributes. It doesn't mean the same name. I don't care about the names. I talk about the number of attributes, and both of them must have the same type of values. For example, maybe you're going to say the ID and name. And maybe here I have an employee, ID, different name, and here employee name. So if you take a look here, both of them have the same number of attributes. The first condition passed. The second condition said must be compatible. This means the first attribute with the first attribute, because when you combine them, we're gonna put the relation R, the list of attributes R. Then after that, I will add in the bottom the list of, let's say, or the instance from the relation S. If here you have different, you join ID with, and one tuple, set of tuples is gonna contains information of the ID, and the rest maybe contains information about different data types. So the data is gonna be, does make sense when you combine them, yeah? So anyway, here the ID with the employee ID, both of them the same domain, both of them talk about the employee ID, so different names, I don't care, as long as the same data type. Here name, this employee name, I don't care about whether there are different names, but the most important thing, they are the same data type. Okay? How about we try, for example, another example here. Let's have, I suppose leave R. Let's say ID and name. And the relation S is gonna have contains information. Let's try to have weird information. Department name, building. Can I perform union between of them here? The first condition, it's okay. The same number of attributes, both of them is fine. The second condition is that must be have compatible. These are domains. The first domain here, take a look here. The first one is what here? The first domain looks like ID. Here, department name. When you combine this one, let's give you example one, Alice. Okay, and this one, computer science, and let's say Stuart building. When you combine them, this is the result it's gonna have. I will add, can I write this one here, just for example. When I said R union S, so you have ID name, one Alice, and the second maybe computer science and Stuart. Do you think that's useful information you got here? No, because we try to extract. That's why I said must be compatible. Okay, maybe someone has asked. So okay, what if both of them they have compatible data but different names? In this case, we have to use their naming. We're gonna cover this one. So the most important thing I want from you to understand this: have conditions. Two conditions must hold in order to perform union between two relations. The same degree or the same number of attributes. We don't care, different names is fine. The names, attributes, then must have, these domains must be compatible. They have the same data types, the same values. In order to, when you combine them, I have a useful result. Let's have an example here. So this example, you have two relations, R and S, okay? And the value are AB and AB here. Both of them the same data type and the same, let's say it's number of attributes. So I can join them, yeah? Combine them. So in this case, what? You're gonna take the result gonna be, the outcome, it's gonna produce, take the relation R, the first one, then after that, just add the attribute that is not exist here. So in this case, actually, when you try to add this one, maybe you have alpha 2 and you have another alpha 2, yeah? But remember, if you have a duplicate value, you're gonna only keep only one of them. So that's the join relation, or they combine both of them. How about, what if we have here, let's see different name, D, okay? In order to perform this operation, since we have a different attribute names, I don't know, or know, for example, what's the name it's gonna be produced here. So the best thing to perform that, we're gonna see later, we're gonna use renaming. So I'm going to rename either the attributes in S, it's gonna be like A, or after I perform, the union, I can control or specify what's the name of the attribute gonna be after I perform this operation. So it's fine if you have attributes that have a different name. So we're gonna take care of this one later when we talk about the renaming, which allow me in order to modify the name of the attributes. Okay? So let's have example here using the university database. I've said find all the courses taught in fall 2009 semester or in spring 2010 semester or in both. So interesting here. So here, of course, I just give you the relation that we need here. Just speaking, the university database, we're gonna much clearer for us when you talk about the data design or database design. You're gonna see how can we extract the information, why we need the section relation, etc. Generally speaking, the section relation is gonna do what here? It's gonna capture the information that, for example, every single course taken by every single student and when the student take this course. It's gonna keep tracking for the section that belongs to each course. For example, in, let's say, the first one, we have a specific, let's say, CS101. We offer this one in the fall, 2009. This is the building, this is the room number, and this is the time slot. Time slot, you can assume that it's going to be from 8 to 10. This A from 10 to 12, B, and C is going to be 12 to 2, and etc. Okay, the time when we offer this one. It might be we have, for example, for the specific course here is going to be offered 2 sections or more sections. So we keep tracking all the information, where it's going to be held, maybe different time slot, and etc. Okay? This is information that captured in the section. So I said all the course taught in the fall 2009 semester. All this information, I'm going to find it here in this section here. So how can you answer this query here? So it looks like you have many queries. The simple thing we can perform here, I can easily find all the list of the course that in fall 2009 semester offered that or taught in that specific time, and create another relation which is going to take find all the course taught in the spring 2010. Then I'm going to combine them or union them. Okay, because what does that mean, union? They said course taught in 2009 fall or in spring or in both. Okay, how can you answer this query? This is the way can I perform that. So first, I'm gonna find this one, gonna produce the list of the course offered in the fall and in the year 2009, which satisfies the first condition. The second one is going to produce all the costs taught in this spring in 2010. Okay? When you said union, what does that mean? It's going to combine this cost, the list of the costs offered this semester, plus the list of costs offered this semester, or either offered here or offered here. So we're going to satisfy this condition that we have. So if you take a look at the instance of the data, the first query is going to be just show you the cost taught in the fall 2009. So I need, what's the fall 2009? This one. Okay, because fall 2009, do you have fall 2009, the second one? Okay, and the third one here. So the first query, or the first relation, let's assume this R, it's going to produce the cost ID. I project the cost ID for simplicity, okay? So you're going to be CS 101, CS 347, and physics 101. The relation S is going to just find out the course offered in the spring 2010. Use different color. Spring 2010, I hope there's not a lot. The first one is going to be CS 101, and the second, the third, not too much, the fourth, the fifth, the sixth. So let's do this one here, this one, I'm lazy guy, and this one, and this one, and this one. Now perform the union. If you union, CS 101 is going to be only one of them, CS 315, CS 319, CS 349, and this one, and this one, and this one, and this one, which is the result that you're going to have here. Okay? I project the course ID for simplicity. You can perform this one. You can remove this one and put this one after you perform this operation. But for simplicity, we prefer to reduce the number of tuples, the number of attributes that allow me in order to perform the operation. Clear, guys? How can you perform union? This is one way in order to perform that. Thanks, guys. That's all for today.